Let's go into the next part. So this is something ridiculous, I know, but if you think about it, by our definition, this is true, right? For those cat fans in the room, this is absolutely true. Think about it, right? Things that have constant volume, but the shape adapts to the container we defined as a liquid a minute ago. So by definition, this cat takes a different shape of the container, so this cat can be considered to be a liquid if we want to. Obviously, nothing else, really, it's not really liquid, right? But a mouse, the same thing. Anything that can adapt its shape to fit the container it's in, but has a constant volume, could be considered to be a liquid. Why is this not a liquid, though? What's our definition of a fluid in the first place? What was our definition of a fluid in the first place?
It doesn't move its shape.
Yeah, and it can, what else was the other part? The molecules.
Oh, it just doesn't have a definite volume.
Okay, but more than that, what was our definition of fluid? We talked about the molecules' motion.
They move past each
They readily flow past each other. Obviously, that's not happening with a cat, okay? You would need physically something flowing to have it be a fluid. Yes?
In this discussion, we're not considering solid terms.
Yeah, we're really not even getting into solids at all here. We'll mention them in the next slide or two, actually, but we're not going to do anything with solids. What we'll do with solids is talk about what happens if a solid is submerged in a fluid. Does it sink? Does it float? Why? Why not? Is it in limbo? We'll get to that for sure. But we are really focused on fluid mechanics here. But, I mean, they involve solids also, but it's not, the focal point is not solids. Let's talk next about density for a minute. Now, in middle school, you are taught mass density, and that's all you're ever taught in middle school is mass density, the second definition. But density as a whole is really just concentration. So if I were to clean up around my house, I happen to make my own house cleaner at home. I know, it's ridiculous, but you can do it, save money, and it's a little bit cleaner. So I make my own cleaning fluid, and I have an actual gallon water container filled with the cleaning fluid. I then pour it into another container to use to spray when I'm cleaning. But it's a much higher concentrated value. So I make the cleaning fluid so that it's like 1 part cleaning fluid, 3 parts water. So that when I actually use the cleaning fluid, I fill up 1/4 of my bottle, I take the other 3/4, put water in, shake it up, and it dilutes it to the right concentration. That's density for you. Density is just the amount of something in a given space. That's all it is, the amount of some substance in a given space. And that space is usually volume. But I can think about population density on a map in social studies class. When you see population density, you see different colors on the map, right? That's the amount of people per square foot or area. That would be people per area. This is mass per volume. So density is a proportion, really, of how much you have of something in a given amount of space. In a given amount of space. If we suddenly took everybody from Mr. Joseph's room and brought them over, the population density in this room might double. It might go up more than double if he has more people than we do. Okay, but density is a concentration factor. Peter the Lane. Answered?
Yeah.
Okay, right.
Like GDP per capita.
Sure. Yeah, absolutely. Any rating as a function of something else's value could really be considered a density if we're looking at spaces. So that's a good one. In economics, there's got to be tons of things that would be considered density.
Density only has to do with mass.
Well, mass density has to do with mass. Again, density is just concentration. So it could be the amount of cells in a given space in a blood clot or some other region, whatever it is. You learn about osmosis, don't you, in bio? Where the fluids can flow through the semi-permeable membranes and eventually they become like in a state of equilibrium where the same amount of concentration is on the outside of the cell membrane and on the inside. Well, that's exactly it. Not that you guys should ever do this, but whatever, you're going to be adults in college. When people drink alcohol, what happens? Their actual cells, they dry up, literally. They dry up. It's a dehydrant, which is why people, when they're adults, when they're drinking alcohol, the next day you'll see them drinking a lot of water all day, right? Or they're drinking water. Because the concentration inside of their cells is so low. They need water to flux into their system so that they can get that amount of fluid in their system up so that they're not dehydrated. It's density. That's all it is. It's the amount of fluid in your body compared to the volume of your body. Again, density can go to any extreme, but you can think in this course of mass density. Mass being measured in kilograms, volume being measured in cubic meters. Another unit of volume, anybody know the unit of volume in the SI system? It's not gallons. Liters, very good. A liter is the same thing as a cubic meter. A liter is the same thing as a cubic meter. Okay, volume. Now, we're looking at, in the English system, gallons, right? Gallons is our unit of volume for the English system. And we know gallons become half gallons, become quarts, become pints, become cups, and you can just have them all the way down because we go on the powers of 2 then. Okay, but we're going to specifically be using kilograms per cubic meter. Actually, is a cubic meter the same thing as a liter? Can somebody Google convert that real quick? I think a cubic centimeter, I think, is a milliliter. Maybe I had that mixed up. I don't want to give you the wrong information, so just check that real quick. Do like 1 liter to meters cubed or 1 meter cubed to liters. See what the conversion is.
Cubic meters, 1,000 liters.
Okay, so it's off by a factor of 1,000. That's why. Okay, so I think it's then, check this one, milliliter to cubic centimeters. I think that's the exact conversion used in chemistry. Try 1 milliliter to cubic centimeters. I think that's a 1-to-1 ratio, right? Yeah. Okay. So that's the one I was. So it's not meters cubed to liters. Sorry. It's a cubic centimeter. Centimeter by centimeter by centimeter is 1 milliliter. 1 milliliter. A cubic centimeter. Anybody know a good object that is a perfect cubic centimeter, almost perfect? A cubic centimeter is 1 centimeter by 1 centimeter by 1 centimeter. It's a little cube. Sugar cubes. Sugar cubes are traditionally about 1 cubic centimeter. It's about a centimeter by centimeter by so just to give you a visualization. That's what a milliliter is. When you measure milliliters in a beaker, when you want to figure out the volume of an object, you drop it in water. You see how much the water level rises, right? That's in milliliters, which is the same as cubic centimeters. We are going to focus on this now, okay? Cubic meters for volume, that is. How about this on the left? This symbol is pronounced rho, R-H-O. R-H-O. It's pronounced rho. It's drawn like a lowercase p, but you don't really include the little extra piece. So watch how I'm going to draw this. Start at the bottom and loop your way around like this. Okay, start at the bottom, loop your way around like this. That's the letter we're talking about. Start here, loop your way around. My angle is different each time, but you're not making a lowercase p. And that equals, again, mass over. Now volume, some students in my class like to do this. Take a look. To designate volume, because capital V can be voltage, lowercase v is velocity. So if you want to specify volume and you want to make sure you understand it clearly, you want to put a little dash over each to remind yourself that this capital V is indicative of volume. Indicative of volume, okay? And the way this doesn't matter, but when I wrote it this way, I used to think there's 3 parts. 1, 2, 3. The volume is meters cubed. 3 parts, 3 dimensions. Okay? Now, in your chemistry course, do you remember Boyle's gas law? PV equals nRT, or PV over T equals PV over T. And the idea behind it was that pressure, temperature, and volume were all related to each other. So, for example, if I have a container, and we're going to use this as an example tomorrow, I think, actually, in your class. If I have a container such as this, and I apply enough pressure to it, eventually what will happen? The top will probably pop off. But let's imagine the top couldn't pop off. And I apply so much pressure, what will happen? It could explode, but I guess it could explode, that's true. Okay, let's do it this way. Top is off. Apply enough pressure, what's going to happen to it? It collapses, right? It implodes. You're right, it was explode with the cap on. With the cap on, it would explode. But with the cap off, it would implode. It would implode. I-M-plode. Now, the idea behind that is that container is what we call compressible. Compressible. Gases, for the most part, are compressible. If you apply more pressure, the volume shrinks for gaseous materials, for gases. Now, liquids and solids are ideally assumed to be incompressible. Liquids and solids ideally are considered to be incompressible. Incompressible, not compressible. This is actually very important for all the equations we're going to use in this chapter. So Newton was a big proponent of fluid mechanics. Newton studied everything in fluid mechanics. Besides, I mean, he was a calculus guy too, but he did a ton of fluid mechanics. And we actually call fluids Newtonian fluids. We call some other fluids non-Newtonian fluids. And I'll talk about some of those in a minute. I can even show a quick video of some of those. Something such as what's called oobleck. If you've heard of oobleck before, it's a material that changes properties under different stresses. It's very cool what it exhibits. But those are non-Newtonian fluids. We are studying Newtonian fluids in this course. If you go to college and become a mechanical engineer and you get your master's focus in fluid mechanics, you will absolutely go way beyond what we're going to do. But even into fluid mechanics in college, the stuff I'm teaching you holds true. Even through into engineering and undergrad, I did a lot with fluid mechanics in college. 2 undergrad courses and then 2 grad courses in the area. And so I really learned a lot specifically in this technique. We're going to go into a lot of the stuff that I actually learned in undergraduate engineering in this course. Okay, so it's a lot of preview of that. Yeah. Oh, sorry.
Is water like that? It's like under different temperatures?
So we're assuming temperature is constant here. Absolutely. Yeah. When temperature changes, the volume changes for sure. When ice freezes, it actually expands, which is the opposite of most materials. Usually when they freeze, they contract. Ice is different because of the hydrogen bond. But yes, the idea is that we're assuming that these things are not changing temperature. So for example, I saw another hand. Give me 1 sec. We're going to use this tomorrow as well. We've got what looks like a little bladder. It's a bladder filled with water that's hooked up to what looks like an IV. And you've seen these before. When you're on an IV, the IV's hung up here, right? So the IV drips into your arm. We're going to look at this tomorrow and see what happens. But there's a fluid inside of here. This fluid is incompressible. If I push down on this end enough, I need to really put a board here, my weight. What it'll do with the pressure, and I'll do it tomorrow more, it'll lift this side up, and it'll cause the fluid to actually fill this little chamber. Right now, I just pulled the fluid out of there. When I push back down here, it pushes that fluid in, which is putting the fluid into the bladder. But this is a closed system. So this system as a whole will not change in its density. We can say that it is incompressible. It is a liquid or fluid inside of there. So liquids and solids are deemed incompressible. Kevin?
So wait, what does compressible mean?
Meaning you can compress it physically. Its shape can easily change. It can be reduced in volume. Think about a gas. You have a balloon. You could take a balloon and squish it enough until eventually it'll pop, right? But you can probably get some of the volume down a little bit. Think about here. Best example. A piece of tin foil after being used. What do you do with it usually? But before you throw it out, what do you do with it? You crumple it up. By crumbling it up, isn't that compressing it? You're taking something that could have been, imagine you take one piece of tin foil and make a little ball out of it or a rectangular solid, and then you just get upset and you crush the whole thing up. You go from a volume of whatever this is to a volume that's like this, right? That would be compressible, the material itself. Now, I know aluminum foil is a solid, so we're like off target there because I said they're not compressible. But the shape is what's compressible in that case, okay? Questions at all? Okay, know our units, kilograms per cubic meter. All right, let's jump into an example of this. You could easily do this on your own. Write down your givens, please. Write down your givens, then go on to write down the one formula we've learned this chapter, meaning chapter 12. We only have one formula so far. You have givens, one formula, you have to be able to solve this, right? You've got some givens, you have one formula only. Marco, what's one of the givens? What's one of them?
We have the math,
Which is?
250 kilograms.
Good. Mass is 250 kilograms. Let's list that first. Something else? Something else? What else is given? Go ahead, Alex.
Density is 1,250 kilograms per meters. Cubic.
Good. And you can use cubic meter to say that if you'd like to. Just like square meter or square yards. Okay, so we're given density, we're given mass. What are we trying to find? What are we trying to find? Volume. Okay? Trying to find volume. So we could resolve our formula for volume if you want to. Density equals mass over volume. So if I resolve this for volume, volume equals mass over density. Okay? a very, very, very simple problem to start. They're not going to be this simple, I'm telling you now. This is like 6th grade math class, okay? Or science class. You learn what density is. Okay, just replace those variables.
So what do you put the volume in?
So we are trying to figure out the volume.
No, what unit do you put?
Well, you tell me. Look at your units of the others. What cancels? What are you left behind with?
Meters cubed.
Yeah. Yes. Will you have to write the V with the little things? No, I'm just doing it to specify that it's volume and not voltage or velocity. No, you don't have to at all. Kilogram cancels as a unit. I get 1 over meters cubed. See how the meters cubed goes up to the top? That's your unit now. Okay, this is really leaving behind a 1 as a unit. 1 over meters cubed in the denominator is putting a meters cubed up in the numerator, really. 250 over 1250, you should know that. 25 out of 125, what is it?
20%.
Yeah, 20%. Okay, 0.2, 1/5, any of those. That's the simple volume here, okay? Be able to manipulate your volume formula, your density formula. That's all I'm getting at here. Is that clear? Be able to manipulate this formula. You will have to. You will probably have to solve for mass at some point, and that just equals rho times V. Again, mass equals density times the volume. Volume equals mass over density. Just be able to manipulate this formula because you're going to have to do it for much more complicated problems than this. Okay, than this. How are they related? This is clear. We did this earlier in the year. Remember with the bottle? Remember with the water bottle with the soy sauce packets? Squeeze the bottle and stuff? It was the first thing we did all year. Almost the last thing we're doing here. How are they related? Mass, volume, density. Give me some relationships. Alex. As mass goes up, density goes up. Agreed. There's more substance.
If volume goes down. No, if volume goes up, density goes down.
Good. You could have said it either way. If volume goes up, though, your density goes down. Let's talk about this for a second before I jump into another example or go too fast. If you were swimming in a pool, right? For those, how many of you have swum in an in-ground pool before? Have you ever tried to get down to the bottom of the deep end? It's pretty tough to stay down there. You notice that? Swim down to the bottom. It's pretty tough to stay down there because what do you do before you take a deep dive? I gave it away. What do you do before you take a dive? Take a deep. And what are you doing by taking a deep breath? My volume is increasing. If volume increases, what happens to density? It decreases. If I'm not dense, I'm not going to sink. Okay? So when people call you dense and they mean as an insult, just say, oh, I don't need help now. That would be stupid insult. But yes, you would sink in water. It would be dense. Yeah, I guess it's not a good way to combat this. Yeah, it's not, no physics. But your density indicates whether you sink or float. So if I wanted to sink, what should I do? What should I do if I'm in the water? I take a deep dive. I should exhale. I should blow out all the air in my lungs because when I blow out all the air in my lungs, my volume decreases physically. You see the difference. That's when you have air in and then breathe it all out. Your chest, literally, your diaphragm stops expanding there. So as a result, you have less volume when you breathe the air out. If the volume goes down, the density goes up, and you will stay at the bottom of the pool. It's not a joke. Try it sometime. Blow out all the air in your lungs when you're already kind of at the bottom, and you'll stay down there at the bottom of the pool. If you do it in salt water, you probably won't work out as well, because salt water is more buoyant. It causes you to float, which is why you float in the ocean for the most part. Has anybody been to the Dead Sea? Okay. Anybody know about the Dead Sea? What do you know about the Dead Sea? Very salty. So therefore what? You float. The density of salt water is much greater than water, and humans can physically float on their back. You can try and dive down. It's difficult. It pops you right back up. It's like holding a beach ball under the water regularly. What's going to happen when I let go of the beach ball? It's going to shoot right out of the water. There's more buoyant force pushing up than the weight of the beach ball pulling down. So it's going to naturally have a net force acting up and shoot out of the water. Okay, so we're going over the quick mechanics of this before I get into them right now. Yes? So let's talk quickly about buoyant force now that we've kind of alluded to it just now. The buoyant force is very much like a normal force. Very much like a normal force. What is holding me above this ground? The floor pushing back with a normal force. So if I take a ping pong ball and drop it in a bucket of water, what's going to happen? A ping pong ball. Think about it logically. In a bucket of water. Yeah, it'll bob, but it'll stay at the top, right? It'll eventually come back up. So I could push the ping pong ball into the water, it'll float to the top of the surface. How come? Buoyant force. The buoyant force is a push upward from a fluid that it's submerged in. Right now, at this moment, the air around you as a fluid is pushing you back up a little bit, actually. Believe it or not. The air around you is pushing you back up, but with zero magnitude when compared to the acceleration of gravity pulling you down. Your weight is so much more than maybe the 0.01 pounds of buoyant force pushing me up right now, that I weigh like 160 hypothetically. 160 down and 0.1 up. Do I notice it? Do I notice buoyancy? No, I don't. But if I go to the moon, and I jump for a lot longer because gravity is a lot less, and there's still buoyant force there in the moon. Actually, on the moon, there's probably not buoyant force because there's no atmosphere, right, on the moon. Is that correct? So there wouldn't be a buoyant force on the moon, actually. So that's wrong. There's not going to be a buoyant force there because you need a fluid to provide a buoyant force. You need gas or air or liquid around you to provide a buoyant force.
Why does it's off topic, but why does Diet Coke float and Coke float?
Different densities, same exact thing.
Or like what's in it?
I don't know, the chemical makeup, it's aspartame versus sugar. Sugar is more dense. The sugar is absorbed by the water, but in those other Diet Cokes, it's aspartame. It's like this synthetic sweetener that pretty much gets you hooked on sugar. Don't drink Diet, by the way, if you haven't noticed that. It's so bad for you, it's unreal. Guys, any of these 0-calorie things that are out now that taste sugary and you're like, oh, 0 calories, this is great. Be careful. Aspartame, sucralose, look at the ingredient label. Those two things are sweeteners that are 30, 40 times stronger than sugar are. And you think, oh, I'm not having sugar. But the next time you have a sugary drink, it's not even going to taste sugary to you because you're used to aspartame. You're used to that kind of a diet drink that actually has all that stuff. So just be careful. The best thing you could have, honestly, it's not good for you, but it's cane sugar. So real cane sugar, so for those, like if you've been to other countries that have soft drinks and you get, kind of soft drinks, like if you have like Fanta or like some other soft drinks from other countries, they have pure cane sugar in them. But a lot of sodas here use high fructose corn syrup. So soda's terrible for you, and then diet soda is just as bad for you, if not worse. So pretty much stay off soda. Yeah. Drink water, drink natural occurring juices. Milk, we don't need. We talked about that one yesterday, right? You guys have to go?
Yeah,
Why are you getting out? Baseball doesn't get out early. We have the same game. We have the same starting time. I'm kidding. I'm giving you guys a hard time. Good luck. Do well. I need to still get changed though. So I'm not even. I still have to get changed for our game. Hey, so listen, ladies, we're gonna get to at least the next slide. Okay? At least the next slide. Definitely cover this because this is material we're gonna cover tomorrow and continue with. So, buoyant force is reaction. Now, if I am in the water, good luck today, ladies. If I'm in the water and I draw a free body diagram, buoyant force pushes up, weight pulls down. Buoyant force pushes up, weight pulls down. If my weight is more than buoyancy, what's going to happen? If my weight is more than buoyancy, what will happen to me? I will sink. But there are times when the buoyant force can equal your weight, and then you would float. The buoyant force won't be more than your weight unless you're holding it under the water and then let go. Because at that point, you're holding it down, and then when you let go, your weight is very little, and the buoyant force is really high because you're holding it down. That's what causes it to shoot out of the water. But if you're floating on the surface, these are in equilibrium. What is apparent weight? It's what you feel like. So, for example, astronauts train underwater because they lose about 80% of their weight when they're underwater. And look at that. The moon is about 20% of Earth's gravity. So if I want to simulate 20% of the gravity I feel on Earth, I would want to be underwater so that I have a little bit of help from the buoyant force. So let's say that I normally weigh, or a person, a body, weighs 200 pounds. but the buoyant force pushes up with 170 pounds. What would my apparent weight be as a result? What would it be? 30. My apparent weight would be 30. I feel like I weigh 30 because the buoyant force is giving me a little bit of support. That's why it's so easy to float and to tread water and to even like doggy paddle, because the buoyant force is doing most of the work, not you. You're not doing most of the work. The buoyant force is. Okay, the buoyant force is. Let's go to the next slide. We'll probably finish on this today, maybe get to the next slide. Archimedes' principle. There are two things. First, the one that you learn about with Archimedes when you're younger in science is that when you get in the tub, the water goes up. When you get in the tub, like a bathtub, the water level goes up. And you use this knowledge in your middle school science class if you wanted to figure out the volume of an amorphic shape. If I want the volume of a cube, it's easy. Oops. If I want the volume of a rectangular solid, such as a cube, what formula do I use to find the volume? What's the formula for a rectangular solid? Length times width times height, sure. So you know what? This brick or this object that's being lowered into the fluid, I could just calculate its volume by myself with a ruler, right? But what happens when I have, for example, the volume of my leg from here down? Good luck calculating that. I mean, literally, from knee down, this is like a circle that gets narrower, that turns into a weird shape. You can't get the shape of the volume of your lower leg by measuring, but you could take your lower leg, right? Dip it in the water, here's water level, until my leg is in the water, see how much the water went up by, and as a result, that's the volume of my leg. That's the beginning of Archimedes' principle. Okay, the beginning of the concept of water displacement or fluid displacement, like displacement in this course, but now instead of displacing a certain length, we're displacing a certain amount of volume.
Oh, it was graduated cylinder, right?
Yep, graduated cylinder, that's right. You would look for the meniscus and see what it went up to from where it started. That differential showed you how much volume the object had.
Once we see how many milliliters the water volume went up, we would convert that back into like centimeters.
Sure, absolutely, yep, absolutely. To see what the volume would be in centimeters cubed, yep. Now, the second part of Archimedes' principle is what we're seeing here. And this is the crux of what we're going to use this whole chapter. The crux of what we're going to use. The idea, actually, you know what? Now, what comes out of here is a fluid, and in this section, we're going to be differentiating between objects and the fluid that they're submerged in. So we're going to have to use a lot of subscripts throughout the process. So whenever we talk about an object, we're going to use O. Whenever we talk about a fluid, we're going to use F. So I'm going to call this M with a subscript of F. What's up, Peter?
Ooh, I just say weight.
What did I say? Weight? Weight. Force due to gravity. Weight. The weight of an object. Mass times gravity. So the weight of the object physically, or the weight of the fluid rather that's being displaced, is going to equal the amount of buoyant force pushing back up. So in this case, when we're trying to find the weight here, we can replace mass now. And we can replace mass because of this formula from yesterday. Solve what's in yellow for mass. And we're going to do this a lot, by the way. We're going to use the equivalent value for mass a lot. So let's solve for the variables. Move the v up. We're going to get rho times v. We're going to get rho times v. So I'm going to replace the mass portion right here with rho times v. I'll use subscripts again to refer to the fluid itself. So the weight, again, the weight of the fluid that's been pushed out is however much has been submerged. That weight equals mass times gravity, but mass is density times volume from that formula up there, solve for mass. So density of the fluid, which is here, times the volume of the fluid, which is here, times gravity, which is on Earth, will give us the amount of push up. So push up from that fluid. So in the very beginning of this, I can actually say, this is what the buoyant force is. Again, the buoyant force is equal to the weight of the fluid that's been pushed out. Weight is mass times gravity, and then we replace. So the formula on your formula sheet that you're going to see is simply this right here. Okay, you're going to see this equals this on the formula sheet. Buoyant force equals density of the fluid times volume of the fluid displaced times gravitational constant. Times the gravitational constant. Okay, we're going to utilize this a little bit. Yeah, the 2 boxes. Yeah, it's 2 boxes full.
You can almost open it with them.
Now, when we use this concept, we have to consider the fact that the buoyant force sometimes pushes up with enough to get the object to float. Other times, the buoyant force isn't enough, and the object then sinks. So we're constantly in this like battle between the buoyant force upward and the weight of the object downward. Okay, we have to keep that in the back of our mind. So at all points in time, we're really looking at a free body diagram that really just looks like this. The weight pulling down and the buoyant force pushing back up. There's always going to be that battle, but the question is the weight too much for the buoyant force? If it is, it sinks. If it's not, it floats. So if we skip ahead to the next slide here, we see sinking versus floating, and that's exactly what we're going to talk about now. So if I want to think about, again, sinking versus floating, I've got buoyant force, I've got weight. I can say that my net force is equal to the weight, well, in this case, is equal to the buoyant force minus the weight. F net equals ma, or F net equals the sum of the forces. Fp pushes up, Fg pushes down. So the difference between these will be my net force. If the buoyant force is enough, these values are going to be equal. And then my answer is just 0, which means that the person or the object is indeed floating. So let's talk about those 2 scenarios now. So let's start with sinking over here, and then we'll talk about floating over here. So again, when it sinks, we know that the weight is more than the buoyant force. When it sinks, the weight supersedes the buoyant force. It's too heavy. It cannot float. Which is what happens when you're on a rowboat, right? If you're on a rowboat and it's floating, but then it springs a leak, over time, what happens to the rowboat? It starts to... Yeah, because what happens to the water level inside the rowboat? It fills up more and more, right? If you have a hole in the rowboat, like a can't patch with gum or something, the water's coming through, it's filling the rowboat up more and more, which is increasing the rowboat's weight. Once that weight is enough, it will exceed the buoyant force and it will then sink. So if we want to talk about floating is kind of the opposite, but we can't just reverse the inequality symbol. We can't just say FB is greater than FG, because that usually doesn't happen. If FB was greater than FG, you'd have a net force upward and this thing would come shooting out of the water. And I think I gave an example yesterday with the beach ball, right? I said if you hold the beach ball into the water, hold it, the buoyant force is really strong. As soon as I let go, the weight of the beach ball is very little. It was me holding it and kept it there. So the weight might be like 1 pound, and the buoyant force might have been 30 pounds. So I was holding it with 29 pounds of force. As soon as I let go of my 29 pounds of force, the 1 pound pulling down and the 30 pounds of buoyant force up will cause this object to shoot out of the water. But we're really focused on when it's floating, not when it's escaping the water. So if it's floating, it's in a state of equilibrium. So these are balanced when it's floating. So we're using equals symbol. What's up, Peter?
I would say equal.
It's got to be equal, yep. Okay, it's got to be equal in these cases. Now, the second piece I want to jot down is what I think you learned in your 8th grade physical science, 7th grade science classes, which is about density. When does an object sink? When you fill in the blank, use the word density in your answer. When does an object sink? When does it sink? Ed?
When there's less dense. When it's more dense.
Go either way. You got to be more clear with the statement. What do you mean? What's less dense? You didn't give me a specifying characteristic. The object, the water, what?
Like if the inside is more filled up, like it's more solid.
Okay.
But
So
it's like air inside and it will flow. Like less weight.
okay, so can we make one statement, Alex? Just one statement alone. The object will sink if... Help him out.
Like the mass per certain volume reaches a certain threshold.
Okay, but that's way too much words. I said use the word density, right?
If density is less than 1.
No, you're assuming things are one. Come on, that's not true.
Water is it 1?
Water is. We're always in water. Right now I'm not in water and I sunk. I'm in a fluid right now. We're all in a fluid. And we sunk to the bottom of that fluid. Did you not realize that? Remember, gas is a fluid. Gases and liquids are fluids. So technically, if I drop a person from 10 feet above, they are sinking in a fluid, but they're sinking really fast because that fluid, air, does not provide a lot of buoyant force at all because the density of air is very little. So when does an object sink? We use the word density. I want one concise statement. That's it. When the density is greater than the fluid's density. That's all that matters. So sinking has to do with the density of the object being greater than the density of the fluid. Okay, just like this. The weight was more than the buoyant force, right? You see how it's analogous? The weight is really a function of the density of the object. The buoyant force is a function of the density of the fluid. And if you don't know that, think about the formula from the previous slide we just wrote down. On the previous slide, we wrote buoyant force equals density of the fluid, volume of the fluid displaced, times gravity. So the buoyant force is a function of this. The weight is a function of this. How about floating? This one's a little bit weirder, because there's two scenarios really. There's two scenarios really here. Give me one of them. What would cause something to float? Density, just density. No buoyancy right now. Let's just work on density only. Yes, exactly. So the reverse of this is one way we can say. When the density of the fluid, or we'll start with the object's density is less than that of the fluid. So it's, these are opposites of each other. When the density of the object is too much, it sinks. When the density of the object is less than the fluid, it floats. There is a third scenario, like an in-between. And this has to do with an object's density being the exact same thing as the water. If they're identical, that object will kind of be in limbo. It won't be floating at the top. It won't be at the bottom. It'll kind of be in between. And you can try this out. And I think somebody actually is going to try it. Andre said he's going to. We'll see. He said he has access to a pool. So the way to try it out, honestly, is if you're in a pool. You can literally, from a certain location, you get to about halfway under, so here's the surface, here's the bottom of the pool, get to about here, and try to blow out just enough air so that you don't sink, but you don't float. Because if you have too much air in your lungs and you're halfway there, you'll eventually start to float. If you blow out all the air in your lungs, you're eventually going to sink. Take a look over it really close. So this object had water in it. The water was heated. The heating of the water increased the pressure inside. Gus then, let's turn this lights on. Gus then put the cap on. And take a look at this. Look at the object. You see can you see from that far away what's happening right now? The entire side of it is imploding. And what's happening physically, when we're talking about pressure in the next section, is that the pressure inside of the can initially was really great. PV equals nRT, Boyle's law. As he increased the temperature of that fluid, the pressure went up more and more. But then eventually, Gus turned the top and closed it. And when he closed the top, what happened was there was a certain amount of pressure, a lot, stored inside. But as soon as he put it in this cold water bath in the sink, because cold temperatures decrease pressure, the pressure decreased on the inside. So right around you right now, you have the atmospheric pressure pushing down. That's physically what you feel. Whether you agree or not, you do feel it. Your body responds to it. Your body is pushing back out the same amount of pressure as the atmosphere. Well, there's a lot less pressure inside this can right now than there is in the atmosphere. So as a result, this can is starting to implode a little bit. And this is nothing more than pressure that's doing it. So right now, the atmosphere is literally causing this can to implode on itself. If you were to be a deep sea diver and you weren't taking care of yourself, you dive down too far, that's what happens to your body. Literally. The pressure of the water will cause your body to just collapse on itself. Good. The bends. Well, that's when you come up too fast, actually. That's not the same. The bends are when you come up too fast and the pressure decreases too quick. Your blood oxidizes and you start to get air bubbles in your blood.
Those submarine cracks.
Jacques Cousteau, those explorers, those deep sea divers.
So how do they
So talk to Ms. Morther about this, by the way. If anyone's interested in scuba diving for real, she's a licensed deep sea diver. She took classes. Ms. Morther had to do a ton of physics and take physics classes to get approved to do this. So you have what are called pressure regulators that you go down to. So if you deep sea dive, you wear a container around your entire body. or at least the upper part of your body. If you're just,
Pressure's released?
it must have popped.
Yeah.
That means
So
that-
this one went more than this one.
Oh no, that's this.
You
Oh,
sure?
no, wait.
It's this.
It is this, you're
I
right.
feel like it's gonna be, see?
Yeah. Maybe put the glove on, take the top off. So, Ms. Boyler took classes on physically learning how to regulate pressure. Because if you're down below the ocean, you have a lot more pressure on you. So as a result, you have to regulate that when you come back up. If you shoot back up to the surface and the pressure suddenly decreases, your body will start to allow, what will happen is the blood in your body will start to oxidize, but the gas from the blood will actually come out of the blood itself, and your body will physically explode. Versus going down to the bottom of the ocean, if you have nothing protecting you, your body would implode. That's why they talk about, like, they can't find wreckage for certain disasters. If it goes deep enough, you can't find bodies afterward. Bodies would be this big. Literally, the entire body is squished down to the size of this small. Think about black holes. Black holes are a lot of mass all crushed down. That's like what's happening when you fall down to the bottom of the ocean.
Your brain melts first.
Is that right?
Yes.
Once you lose oxygen, you're done.
Yeah.
But you think your brain compresses first?
It does, yeah. It's because of your ears. Have you ever gone to the bottom of a pool and it hurts your ears and
That makes
head a lot?
sense.
Imagine that.
The pressure all goes in here, right?
Yeah, so it just goes in right away and just goes and crushes your brain.
Good to know. So that's kind of what Gus is doing. Careful.
I know, I tested it, it's fine.
Oh, okay. Yeah, earlier I did that. It actually saved that quickness. I didn't think that would work. So maybe throw a little water in, cap it, and turn it on so that the pressure increases so we can get back to normal shape. So the idea behind this, I want you to recognize, is that there's always pressure acting down on you, physically, the atmosphere. Your body responds with the exact same amount of pressure. If, hypothetically, we could remove the atmosphere from the earth, everyone would explode. You'd all explode. Because the pressure inside your body pushing out right now is 14 pounds of square inch pressure, PSI. The atmosphere pushing in is 14 PSI. But if you suddenly didn't have the atmosphere pushing in, everything inside your body that's pushing out would literally push out. You would explode. Anyhow, that was today's demo for this. We're gonna learn more about this in the next. You just got to be careful.
Yeah,
because
I want it to blow.
yes, you got to be real careful. As soon as you start to see it get bigger, what you want to do, Gus, take the top off temporarily, let it expand a second, put the top back on, just do it in stages. You know what I'm saying? So it doesn't just suddenly the top pop. Yeah.
Yeah.
Why isn't the pressure of the atmosphere like 15 psi?
Oh, also?
It's exactly what it is.
This is perfect. That, like,
I mean, it's not exactly 14.7. It's like 14.71. It's 101.3 kilopascal. It's measured. You can use a barometer to measure. It just happens to be what the Earth's pressure is. There's no, we didn't pick it or anything. It just happens to be what it
This
is.
happened? It's the cap. It's part of the cap.
Okay,
It was
well,
stuck to the
that's
top.
okay. I guess it won't matter. If you need it, then you use it.
I'm
So-
trying to see if the cold water melts. You need it.
So the idea here is that if we're in a state of limbo, this is the only one that's a little bit weird, is when the density of the object equals the density of the fluid. This is that in-between stage where you're not floating, but you're not sinking at the same time. So the example with the pool I was giving was if you can get enough air out so that you wouldn't be too dense, so you would sink, but you wouldn't be too not dense, too whatever light, that you would float, but you'd be somewhere in between. Somewhere in between. Did I talk about extra credit? The egg? Did I talk about the egg extra credit yet? Okay. So let's talk about this. So I'm not going to go into this today. It's going to be an extra credit opportunity for you. Here's how it works. And the other one was much harder than I told you about. This is a much easier opportunity for extra credit. So you need to get a container that is clear. Put an egg in it. Fill it with water. You want it to have a little bit of room outside of the egg so that if you stir it, you're not going to break the egg. So you might need a plastic stirrer instead of a spoon to do this if you're using a narrow, like a pint glass. But if you can use like a vase, that might work better. So you put the egg in, fill it with water. If the egg is healthy, it will sink. That's how you can test for bad eggs, by the way. If you want to know if your eggs went bad, put it in water. If they float, the egg is spoiled. The gases are released inside, decreasing the density, it floats. So if you want to check that out. So it will stay at the bottom. You fill it with water. Then, over time, what you want to do is you want to increase the density of the water. And the only way to do that is to add substance to it. So what substance do you think you're going to add to it? Salt. Just like we talked about salt water in the Dead Sea, keep adding salt a little bit at a time. But you need to stir it. It's not going to all dissolve. You're going to have a layer of salt at the bottom, probably this thick. You got to use a lot of salt to do this. So keep stirring it, keep stirring it. Eventually, you got to kind of go a little slow though. Eventually, there'll be just enough density in the water to get the egg to just lift off the bottom, but not come up to the top. And you'll be in that state of limbo that I talked about, where the density of the egg equals the density of the fluid. Pause when you're stirring. You'll see the egg in the middle. Then, once you've got that recorded, you can explain what's happening, talk about the density, talk about the buoyant force, make sure it dictate the whole time you want credit. Then the egg, eventually, if you keep adding salt, will do what? Come all the way to the top and float. Because eventually, if you keep making the density of the water more and more and more, the density of the egg relatively will be less. Gosh, you need water in there. Is there
There's
water?
water in there.
Okay. Just make sure here. So that's the idea of this extra credit. Okay, so you guys have to maybe consider doing this at home. Get a vase that's the right shape. Can't use a hard-boiled egg, it won't work. Use a regular egg, obviously. But make sure to explain as you're going through it what's physically happening if you want full credit. It might not work, Gus. It was a hypothesis, I thought. Clonson. Yeah, two of you want to be in the, as long as you're both in the video and discussing and stuff, as long as I know you're both there. I don't want it to be you doing it and someone else gets credit.
So you said you should add salt to everything. Any other like sugar work?
I think it would, but salt dissolves well in water. So that's the reason it's good for it. I think sugar would work though too. You can try that if you want. Probably would. There's actually, there's a science experiment in chemistry. I don't know if you guys did it, where you supersaturate a fluid. So you keep heating it up. You heat up water more and more and keep adding salt. And as you increase the temperature, it becomes more soluble. So more and more salt can get dissolved if you increase temperature. It doesn't settle out. And you keep increasing temperature more and more and keep adding salt. And then what you do is you turn off the heat, you let it sit overnight, and it's a super saturated solution. It's water with an abundance of salt. And when the next day you add one salt molecule, the whole thing turns into a solid. It crystallizes. The entire thing, all those salt that's hidden in all those, I don't know how it works chemistry-wise too much, but all the salt that's contained in the water suddenly comes out of the water and it becomes a solid. Physically, you'll see it crystallize the whole way through. You can YouTube that also if you want to see what it looks like. Did you do anything like that in chemistry last year? I got to tell Mr. J about that demo.
Solubility charts like we used to study. I don't know if you did it exactly.
Solubility tables are what you would be using to know how much salt to put in. Extra credit? It's always before the test. So before your next test, whatever that is. Okay? Yeah. All right, now we need to get into quick things here and then jump right into a math example. So the first thing we're going to look at are just variable densities. And what do I mean by variable? I mean changing. Things that can change the density. How do you know fish can change the density? What's an example? Yeah, the gills. The gills allow them to take in some sort of oxygen from the water, right? Anybody know a certain fish specifically that can change its density very easily? The blowfish. There it is. The blowfish literally uses this as a defense mechanism. So the blowfish, when attacked by a predator, will actually take in enough air that it expands, so it intimidates and makes it look big, like it makes it look like it's strong, but it also causes the blowfish to accelerate upward to the surface. So when a blowfish is trying to escape another fish, it will literally expand and accelerate and move upward. It will also, because it's a defense mechanism, make it look like it's stronger. But fish have variable densities. We've already talked about humans. Humans have variable densities. If I take a deep breath, my density just decreased. If I breathe it out, my density just increased. Because air is not dense. So when I take it in, I'm decreasing my density. Liquids. So we talked about how liquids and solids are considered to be incompressible. We can't compress them anymore. But their densities can change. And we just saw that a minute ago with the egg experiment we talked about. If I add a solute to the liquid and it dissolves, by default, you're increasing the density. You're physically giving it mass and not changing the volume. So you're increasing the density. And last but not least, how many of you, has anyone ever been on a high air balloon ride? Yeah, I was going to say only one person in the class had. I've never been on one.
What about deep sea diving? We're talking about it. They use the thing to bring them back up and back down. We got the little sack.
The air sac that pulls them up?
What you do, you fill it up. It's based off of a fish's gallbladder. That's what the gills do. They suck in the oxygen. This is them.
You seen Waterworld?
I've seen that before, yeah.
That's what he does in Waterworld. Remember when he brings out the other person underwater that doesn't have gills?
Yeah.
Waterworld is this movie where the whole world's covered in water and Kevin Costner has gills and everything. Because he's like adapting over time. So you can swim underwater. So he helps this woman to see what's underwater, like the old civilization of New York. It's all underwater. So he brings her down. He's like, what looks like a bell. Imagine a bell, like a bell you would ring, but a big chamber of a bell. And he attaches a rope and he pulls down on it. So all the air gets stuck in there. So the lady's able to breathe the whole time while she's
People
in.
did that for a very long time.
Before they
They
had.
suppose that Greeks had diving bells.
Is that right?
Yep.
That makes sense. It makes sense. It's the way you do it. So a hot air balloon works with the same premise. A hot air balloon, the idea behind it is that the air inside the balloon is less dense than the air outside the balloon. So what does it do? It floats. And why do you think you pull on a flame? Hot air has less density. So the hot air balloon director pulls a flame, which gives hot air to the balloon, hot air balloon, which is much less dense than the air around it. That's the whole concept behind the hot air balloon. All right, let's keep going though. So I want to get into this math example. Okay? So we're going to calculate the magnitude. We have a couple things to do here. Calculate the magnitude of the actual weight, the buoyant force, and the apparent weight of an iron ball. An iron ball. Like a ball bearing, like a BB. Imagine a BB. Okay, like from a BB gun, those little BBs? Or the buckyballs, like I referenced those, buckyballs? Yeah. So a little BB. So we want to calculate again its weight, the buoyant force acting on it, and the apparent weight. And then after that, figure out how much of the ball is floating. Part of it's underwater, part of it's floating. Let's figure out how much is doing each. So we're going to go one step at a time in this process. Okay? Now, already I need to know some information. On the test, you will not have to memorize densities. I will give you densities. Okay? Any density in the problem will definitely be given. And I didn't write it in this problem, so let me start by giving you densities. The density of the object, which is the iron ball. I jotted it down. I don't memorize these obviously. 7.86 times 10 to the third kilograms per cubic meter. The density of the fluid, which is liquid mercury. Liquid mercury is very dense. It was used in thermometers for a long time because of its thermal expansion coefficient. It was able to rise and lower in a thermometer, but then they realized it's not safe, so they stopped doing that. So the density of liquid mercury, I should say fluid, not object, right? The density of liquid mercury is almost double, 13.6 times 10 to the third. So those are my two densities that have to be given in these problems. So let's make believe they were given in the initial problem. But if not, for homework, what should you do? Look it up. Either in your book, there's a whole table of densities in this chapter, or just Google the density of it, right? But please make sure your units are proper before you use whatever Google tells you. Now, with those values given, we can go into this process. So let's start with the first thing. The first thing says, find the actual weight. And it says magnitude, because I don't care about direction right now. We'll see direction applied in a minute. Gus? No? I hear noise, but it's not. Just be careful.
Yeah.
Just because Alexa's nearby and they're over there, I don't want just in case.
I'm gonna just take it off.
Yeah, I guess at this point it's not working, so don't worry about it. I'll figure out a way to get them back to shape. I'm trying to get them back to explode so I can use it again next year instead of just wasting this, because you're supposed to throw it out and you buy it. But we'll figure it out, Gus. Just take it off the heating element for now.
Use that if I put it in the cold water.
It's going to do it again. Well, just take the top off and it won't.
Yeah.
If you take the top off, it's not a closed container, so the pressure will change. So you just take the top right off. So we want the actual weight. The actual weight, to find the weight of an object, we know the formula is Fg equals mg. That's the weight of an object, right? Now, do I have the mass of the object? Am I giving the mass in this problem anywhere? You're probably not going to be given mass in most, if not all, of these problems. So you're most likely going to be replacing mass with its equivalent variable, which is density times volume. What we just did in the last slide, solve the formula density for mass. So again, I'll write in the top right, solve this formula for mass, and you get density times volume. So let's replace the mass here, okay, the mass of the object with its density times its volume. And this happens a lot. It's not the only time you're going to see it. A lot of problems, we're going to replace mass here with density times volume. Density is given. It's right here. The volume is also given. What's the volume of this problem? What's the volume of the ball bearing? The word volume is not used anywhere, but it's given. It's given for sure. Sarah, good. Yeah, how do you assume that that's right for volume, Sarah? What do you use what's the identifying factor? The what? Okay, that could help. Something else that's way more obvious. Meters cubed. Cubic meters is volume, right? Square meters is area. Meters is length. So as soon as you saw that this was a unit of cubic meters, even though it doesn't say that that's volume, it is the volume. Units, 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 okay? Units help so much, again, to identify what variable you're working with. So that's another one of my givens. Okay, so all my givens are there in black. Right, those are all my givens. On the right side here in red and blue, we're seeing our actual formula. Now we have rho 0, the density of the object. We have V0, the volume of the object. We have gravity on Earth. Just plug and chug. You're going to multiply those three. I'm going to give you the number for now. Okay, but we have all those values. It's going to come out to be 3.86 newtons. It's a weight, so it's in newtons. And again, you can try it on your own on your calculator. It's got to be in scientific notation, so make sure you understand what you're doing. This times 9.81. Now, that's the first step. We've calculated the actual weight of the object. Step 1. After that, what are we on next? Calculate the buoyant force next, right? What's the buoyant force here? Either A, how do I get it? Or B, how is it related to what we just did? The object is floating. The object is floating. So I go up to your last slide. The object is floating. The object is floating. On the last slide, what does it tell us, Catherine? What up? Yeah. The weight pushing down is equal to the buoyancy pushing up whenever it is floating. So you don't need to calculate the buoyant force here. The buoyant force is the exact same value, except in the opposite direction, which is why I put magnitude, right? Buoyant force pushes up, the weight pushes down. I'm not putting positive or negative signs because I asked for the magnitude. Next, what is the apparent weight? How heavy does this ball bearing feel when it's floating in water? When you float in water, when you float in the ocean, in salt water, how heavy do you feel? When you're floating, how heavy do you feel? Right? You definitely feel lighter than your own weight, I agree. But if you're actually floating, Peter,
Weightless.
you feel weightless. That's what floating is, right? The idea of floating is feeling weightless. So what is the apparent weight? The apparent weight is the difference between the weight down and the buoyancy up. But what's the difference between these two numbers? No, there's no difference, right? If I see how much my weight is, and I take away how much the buoyant force is helping me, I can see what my apparent weight is, what I feel like. I feel weightless right now because buoyancy is pushing me back up and causing me to float. So as a result, the apparent weight in this problem, which is defined as F net, is FB minus FG, which equals 0 newtons. F net is always the apparent weight. And the difference between these two. If you weighed more than the buoyancy force, then you would have some weight. You might feel like you weigh 10 pounds. How many of you are certified lifeguards? Or have gone for lifeguard training? Just one, is it? Yeah, I feel like I put those in a thing. Alright, well, give us an example. Did you have to carry a brick out of the water at any point in time? You have to swim down to the bottom, right? Bring the brick back up, hold it. Did you have a little dummy also? So you have to hold the weight above you when you swim up. But did it feel that heavy? You're supposed to say no, Mr. Howell. Not really. No. So it probably felt heavy because it is a heavy object. But did it feel as heavy as it really is? No. It probably still felt heavy. That's true. But if you've ever done this before as a lifeguard, or if you've trained for lifeguarding, if you train for ocean lifeguarding, two of my brothers are ocean lifeguards. If you train for ocean lifeguarding, you have to be able to physically hold someone and swim with their entire body weight. but you're not carrying their body weight because buoyancy is helping push them up a little bit, so you might be carrying a quarter of their weight, really. Okay, about a quarter of their weight. There's no way you can carry an entire person's body out of the water without having fins on or without having like webbed hands or webbed feet. You can't create enough force when you're swimming with your hands. It's impossible. So the apparent weight of anything that is floating is always 0. Last but not least.
So the apparent rate is also, so it's measured in newtons, right?
Yeah, because it's a difference between the buoyancy and the weight itself. And they're both newtons. Newtons minus newtons is newtons. Could be pounds. If you want to use the US system, pounds are force, right?
Right.
Just like newtons are force in the SI system. So the last piece we have to think about now. How much of the ball's volume is floating? So go ahead and draw what you think this looks like right now. Draw a liquid surface and draw a little ball bearing on the surface. The question is, how much of it is floating? Do you think the whole thing is floating? Do you think that's actually really possible for a ball bearing? Probably not. A raft, if you've gone to like a water park, like a tube, a blow-up tube that you go down the water slide in, that whole thing is pretty much floating. Very little bit of it kind of dips into the water. A boogie board, a surf, any surfers in the room? Surfboard, okay. Surfboards float really easily because they are very, very low density. The material is made for that reason. So part of it is under the water. So for this example, the whole thing is definitely not floating. So if I'm going to draw what I think this looks like here, here's my liquid mercury. I'll draw that in red. And let's say this is the iron ball bearing. I don't know if it's half. I just kind of drew like that. I don't know if it's half. That's arbitrary. But I do know this. My goal is to figure out the shaded yellow region. That's my goal, to figure out the shaded yellow region. How much of the volume is physically floating? Well, let's start by answering the following question. How much of it is underwater? Because if I know how much is underwater, and I know the volume of the object itself, what can I do with those two numbers then? Thank you. Subtract. Then we'll get what's left over. So let's figure out how much of it is underwater. But the question comes, what variable is that? What variable represents how much of the object is submerged? What variable represents that? It's very misleading because it's not a very big thing. It's VF. The volume of the fluid displaced, the amount of fluid that's been pushed aside, is always equal to as much of your body. Remember I did this yesterday? Put your leg in the water. If this much of my leg is underwater, then the amount of water displaced is the volume of my leg, not my entire body. So here, if I want to know what that volume is underwater, it's VF. Whatever the volume of the fluid is that's been displaced. So I'm going to figure out what's in black, shaded, and then subtract that value from my original volume to see what's left in yellow. So again, I'm looking really for VF. And then from that, I can find the volume of the object out of the water. How do I find VF? What formula has VF in it? What formula has VF in it? We wrote it down a little while ago. Swipe up if you need to. There's a formula with VF in it. Figure it out. Formula with VF in it. What is it? Peter?
PF, VF, G equals FB.
Yeah, the buoyant force equals this. Now, I'm going to do a little pointing here, not so much math. This is known. It's right here. This is known. It's right here. This is known. It's 9.81. So VF you can solve for you, right? Once you get VF again, that's what's in black. Subtract that number from the total volume to see how much is left outside of the water. Okay, definitely finish this tonight. Make sure to get this example. The homework is not due tomorrow now. We still have to finish up this lesson. Tomorrow we're going to do another demo, finish up the lesson. But you have 6 homework problems in this section. You can do at least half of them at this point. So if you want to get a head start, so you don't feel, I have a lot of things all at one time, because I'm telling you now, this will be due another day from now where you have other stuff also due. So get a head start tonight and work on half of the homework. Don't complain if you have a lab due the same day this is due in a couple days, because I'm giving you a head start right now to get started on it. The body diagram for this one is not just buoyancy and weight. In the example we just did, buoyancy was up, weight acted down. Right? Force of gravity was down, buoyancy was up. That's all we had. But in this case, we don't have just that. So imagine you take an object, this is an example like a buoy. This is how buoys are put in place usually. But buoys are actually floating. This is going to be underwater. But imagine you needed to have some sort of a chamber under the water for some reason. I don't know, maybe it was like a fish feeder, right? You need to be underwater, and over time it would like allow food to come through the membrane, and the fish could eat that food. I don't know, just thinking about something you could have that's tethered at the bottom. So you take an object, bring it down into the ocean a little bit far, tether it or anchor it to the bottom of the ocean, using some sort of like a rope, a chain of some sort anchoring. Then inflate the object. Inflating it enough so that its density is now less than salt water. So if its density is less than salt water, what's it going to want to do? You inflated it, the density is less than salt water, it's going to want to rise, float, right? Now, because there's a chain connected, as soon as it starts rising, that chain will end up getting tension in it, and it'll be taut, right? A taut rope is going on the rope. So imagine the chain literally being pulled. So our object, if we were to draw a diagram, I'm just going to draw a circle for the object, is tethered down with a chain to the bottom floor of the ocean right there. The chain pulls down, the weight of the object pulls down a little bit, and then the buoyant force pushes up. So this is what's happening in this diagram. Okay, when it was dropped to the bottom, it was dense enough to sink, but because it was then inflated, it became less dense than the salt water, so it's going to want to rise or move upward, which is causing tension in that chain. So our goal in this problem is to find out how much tension is in that chain. Why would this be a design problem for an engineer? Logically, use logic, yeah.
So in order to keep it grounded instead of like floating way up to high or like fluids in it.
Yeah, so what might we do with our answer we get here? Because we're going to get the amount of tension in the chain, right? That's what we're about to solve for. What might I do with that answer?
There are different types of materials that make chains and use one split.
Exactly. If you've ever bought rope or chain or fishing line or anything that is like a rope of some sort, chain is really a rope, right? Chain links are really a rope, when you think about it. Anything that has tension in it, it tells you it's allowable strength. So remember the pendulum that you guys had? They were tied to that little fishing line and they would swing back and forth. There's an actual amount of pressure or tension in that rope that's allowed before it'll snap. It's its yield strength or its maximum capacity. So if we can figure out how much tension this chain will feel, well then, as Steve said, we'll pick a material that actually can withstand that much tension. Or else if we pick any arbitrary material, what's going to happen is it might snap, right? The tension might be too much, and the chain will snap, which defeats the purpose of this whole problem. So this is a design type problem. I want you to recognize a simple design, but yet a design still. Right? A simple design, but it is a design. So when I look at this, I start with a free body diagram, especially when there's more forces than just buoyancy and weight. So buoyancy is up, weight is down. What else is down? Is tension. There's my free body diagram. And it's pretty much the same thing as on the right over here, right? I just didn't put the labels on. So tension down, weight down, buoyancy up. The whole idea is that this object inflates but then doesn't move. It moves up a little until the tension in the chain takes effect, and then it should stop. It should stop. It should stop. What can I say because it stops? What can I conclude? It's in equilibrium. When things are in equilibrium, there's a balance of forces. So I could start by saying is equilibrium, which tells me F net equals MA, but this is going to be 0 because it's in equilibrium. I've got buoyancy pushing up, tension pulling down, the weight pulling down, and that's going to equal 0. This is just logic. It's almost common sense at this point. If I take these two forces and add them over, it makes sense with the diagram. Take Ft and Fg. I know we're solving for Ft, so we're going to get Ft by itself in a minute, but just for the sake of this expression or this example, if I move these two over to the other side, that makes sense. That is a balance of force. Buoyancy pushes up. Tension and gravity together pull down. That's the balance that we're seeing here. Again, without the cable, without the chain link, here's what it is, right? And then that question becomes, is it heavy enough to stay down, to not have the buoyancy overcome it? No. So that buoy would float up out of the water now. It would shoot up out of the water, kind of like the beach ball out down. So this problem involves us solving for tension. But I want you to see that you could have gone from here, take a look right here, You could have gone from this and said, hey, you know what? It's equilibrium. Right to there is fine. You didn't want to write these two to start. Because if it's in equilibrium and your free body diagram is correct, whatever forces act up equal the sum of whatever forces acting down, which is what this statement here says. Okay, but the traditional way you see it in physics, right, is the way we're writing at the top to start. But our goal again is to find the tension, so let's solve for Ft. The tension. Come on.
Wait, how do you know it's in equilibrium?
Because if you read the problem, you'll see that it says the chain is anchored. The chain that is anchored experiences tension in the links. What is the force of tension if blah, 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 the details there. So if there's tension in the rope, it must not have snapped. If it snapped, there wouldn't be tension, right? So by default, because there's tension in the cable, you know that it's anchored and it has to be pulled down. And if it's anchored, it's not moving. Think about a boat. You throw the anchor at the boat, right? Because it literally anchors you to the bottom of the floor. It holds the boat from moving. Maybe it sways a little bit, right? But this object is held in place. It's not going to move. This is not a spring, by the way. It looks like I drew a spring. I'm sorry. That's it's supposed to be a chain, so maybe give it like more of a loopiness. Okay, it's a chain like that. There you go. So yeah, that's why this equilibrium here, okay? So when you want tension, we solve for it. And this makes sense. Look at this problem. Look at the mathematical, forget the numbers for a second. Just look at the equation. How much tension is there? Well, it's whatever the buoyancy has extra over the weight. Think about it. If the buoyant force is 100 newtons up, or 100 pounds up, and your weight is only 70 pounds down, are you going to stay down? No. If I weigh 70, but buoyancy is pushing up with 100, I'm going to go up. So that's where the 30 comes into play. The difference in those amounts is what's left over for the chain to hold on to. Again, the chain length is Ft. That takes place of part of your weight. That and your weight together balance the force of buoyancy. At this point, we have formulas for all of these. What's our buoyancy formula from, was it yesterday with you guys? I think, yeah. What's our buoyancy formula? Buoyancy. You could swipe up and look at the previous slide, right? What's our buoyancy formula? Peter?
Buoyancy
Somebody else help him out? Buoyancy equals, what's the formula? It's on your formula sheet. It's on this last slide. It's on the slide 2 slides ago. FB, what's the buoyancy formula we wrote down? Isabel?
FB equals PF VF times G.
Yeah. Okay, rho F, VF, G. The density of the fluid times the volume of the fluid displaced times gravity. Absolutely. Good. Then I want to put the weight. FG always equals? FG always equals? mg. The mass times, yes, I heard 9.81. The mass times that. Now, do I have mass in this problem now? Let's go back to the beginning. Let's look at the actual words. Mass is not given. It's not given. Ray, what do you think we should do if mass isn't given?
Well, we should try to calculate it, right? So, is it just 5 times 2?
Where are you coming up with that?
Well, we have the volume, right? That's the denominator, essentially. And we also have the density, so we're just missing the numerator.
Correct. So we're going back to that formula again. Here's our formula. Density equals mass over volume. And solve that formula for mass, just as Rain said, it's going to be the product of density and volume. So we can replace MO. We've done this once already in the last example. We will continue to do it in almost all examples for this topic. You're given volumes, you're given densities, because those are more the fluid mechanic properties. We're not going to be given the mass needs. So let's replace mass with density times volume. So the formula on the left stays the same. And then I have to put density times volume. Okay, that's what's in parentheses in red there. Density times volume is taking the place of mass. What does the O stand for again? What does the O stand for? The object. The density of the object. The volume of the object. The density of the fluid. And then what's this again? This is the trickiest one. Most people confuse a lot with. What does VF stand for? It's not the volume floating, remember, but the new floating. What, I mean more than that, not just the fluid, because this is in the ocean. You're taking all the ocean's fluid. You know what I mean? Right, this is in the ocean right now, so it's not the volume of the fluid any more than just the fluid. Continue that statement if you'd like. Alex, help her out.
Volume of the outside.
At the outside now.
Like the volume of the fluid that's being like pushed away.
Displaced or pushed aside. Remember, when something goes underwater, the amount of the object pushing the water away is the volume of the fluid displaced. That fish tank over here, right? This fish tank might have 3 gallons of water. But if I go ahead and drop this eraser in there, I'm not going to do it, if I drop this eraser in, I'm not going to use VF equals 3 gallons, right? It's not 3 gallons of water that I'm displacing. Whatever the volume of this is, when it's submerged fully, is what's being displaced. But maybe it's not fully submerged. Let's say maybe, hypothetically, take a look, instead of the whole bottle being underwater, it's just that far. So VF is whatever is submerged. Because look, right now, whatever's underwater is pushing aside all the other water. Whatever's above water is the remainder of this. VO is the whole thing. VF, when this is dropped, the VF is equal to the VO. Because all of this bottle, let me just push it down a little bit, all of this bottle is now underwater. Okay? All of it is underwater here. So the amount of fluid displaced is equal to the volume of the object itself. But when it's only halfway underwater, that means VF is not fully the object itself. It's just like half the object or a quarter of the object. So if you want to write yourself a note, if you don't have this memorized yet, yes, VF is the volume of fluid displaced. But another way to think about it is VF is the amount of the volume of the object submerged. However much of the object's volume is submerged. Again, VF is however much of the volumes of the object's volume that is submerged. So in this case, when something sinks completely, what statement can I make? How much of the object is submerged, Peter? 100%. God bless you. 100%, the whole thing. If half of this object had been submerged, then VF would equal 10. Because look right here. The volume of this object is 20 cubic meters. So if I said that half of it was submerged, then this VF would be 10. If a quarter of this was submerged, this would just be 5. Yes? Does that make sense? Okay, so VF in this case is the same as VO. Whenever an object sinks, you can write this down also. You already wrote it down once, but you can write it again. Whenever an object sinks completely, VF and VO are the same thing. VF and VO are the same thing.
Do we ever have to calculate what percent of the object is submerged?
Sure, you could do that. And to do that, you could just take, ready? If you want to know how much is submerged, you could take VF and divide it by V0, right? You'd have to have a little more information to do it, though.
Right.
Because that's 2 variables, right? So something would have to cancel rain or something along the way. I told the other class, this section we're going to finish today with this topic of buoyancy. We want to do 2 problems. We're going to move on to the next fluid mechanics topic in 12.2 still. But this section, there are a lot more examples you can look at. So if you want to look at your textbook examples from the homework, but I'm also going to put up a document online with a lot of sample math problems for this topic specifically. I would recommend doing them just to get more practice. Because this, I'm telling you now, this is the area that most students on mechanics struggle with, this math part. The buoyancy stuff they have trouble with. It seems to be the harder topic. The next thing we're going to learn is a little bit easier, I think at least. And just looking at student tests from the past, it's absolutely true that this is the hardest topic in 12.2 and 12.3, what we're doing now. It'll get a little bit easier with the other stuff, actually. Yeah?
You said whenever an object is submerged is equal to VF.
VF and VO are the same.
What part of it is equal to VF?
What is VF? VF is how much is submerged. If it's fully submerged, you just answered the question.
What unit of that? What unit of the object is that?
It's volume. The volume of the object equals the volume displaced when it's fully submerged. So VO and VF are the same in that case. What's VO in this case? We're told, right? VO is 20. It's given in the problem. Right here. The volume is 20. Well, again, if it's fully submerged, then VF is also 20. Look what I'm going to write, okay? I'm going to write it all in one line. VF is the same thing as VO because it's fully submerged. This is how much is submerged. This is the actual volume, and they both equal 20. So that makes life easy, doesn't it? Because now these V's are the same. These V's right here are the same. G is the same also, isn't it? Gravity is gravity. It's not changing. What's the density of the object? That's given. 500 kilograms per cubic meter. So what table value do we have to look up? What table value do we still have to look up? It wasn't given in the problem, so if we were doing this for homework, what table value would I have to look up? Look at the last equation. What's missing? No, gravity's 9.81. Steve? The density of salt water. The density of salt water. Density of water is 1,000. Salt water is a little heavier, 1,025. Okay? So what's in blue is not something you have to memorize. You might eventually start to remember the number for salt water is 1025. Water is 1,000. That's one you really should know, but I'll give it to you. I'm telling you now. I'm not going to assume any knowledge from this constants. So your densities will be either in the table at the end of the test or given in the problem itself. Okay? At this point in time, we have density of the fluid, that's salt water. We have the volume, or the amount of the object that's submerged, that's 20. Gravity is known. This is known as 500, this is 20, this is 9.81. We can plug in all of our numbers and get FT. Okay, for those that really like algebraic solutions, if you want to just plug in and get your number, do it right now. But if you really like algebraic solutions, you can actually go one step further. Since the V values are the same, you could factor it out in front. VF and VO look like different variables, don't they? Aren't they listed as different variables here? But if you look at the number, VF and VO are the same in this problem. Right? The volume of the object submerged is the same as the total object, which is 20. So I could technically just get rid of these subscripts because they're the same. And then I have V and G in both these terms, factors out in front, V times G. And then what's left is rho F minus rho O. So if you like numbers, plug in numbers right now. But if you like the algebraic solution, the problem becomes this. Volume, because VF and VO and VF are the same, so I could just put V, times gravity, times what's left over when I factor those two out, which is this. So really, hold on one second, Moses. So really, this problem is all about the difference in densities, right? That's what it's all about. It's all about the difference in densities. If the difference in densities didn't exist, what would the tension be? What would the tension be if the densities were the same? Alex? Zero. Because look, if these were the same numbers, you would get 500 minus 500 is 0. 0 times 9.81 times 20 is still 0. And that makes sense. That makes sense. If I am not less dense than water, then I would assume and probably be in that limbo stage, remember? When they're the same? So there wouldn't be tension in the rope if the density of the object and the water were the same. But it's not true. The object is far less dense, so it wants to float, which is what's creating tension in the cable. Okay, plug in numbers, you will get 100,005 units of newtons. Okay, again, I'm not going to show the substitution right now. It's a waste of time. I trust that you guys are doing well enough this year, you have, that you can plug in on your own, either here or here. Either of these last two lines you can plug into are fine. Either one of them. All right, let's go on to the next thing. So we're going to get through most of the notes. We're going to be on the last topic probably when we finish today. Okay, so again, definitely start your homework for 12-2, even though it's not going to be due on Monday. You still have to finish these notes a little bit on Monday. Okay, but definitely start your homework, do the buoyancy ones, and in a minute we're about to talk about pressure. So also do the pressure problems that you can do. Okay, we'll do another type of pressure at the end that you won't be able to yet. Show of hands, how many people as a child, or even still to this day, have taken dance classes of some sort? Honestly. Male or female, yeah. I wish I had taken dance classes when I was younger. It's a good skill. Gentlemen, if you want to win over ladies later in life, learn how to dance. True story, learn how to dance. I know it's crazy, but it really does help. Anyway, so, and other men and gentlemen, ladies, whatever. Orientation wheel. So, pressure has to do with the amount of area, but I asked about dancing. How many of those that raised their hand have done ballet? Okay. So when you try to get up on those tippy toes, what's that called? Do you know the name of it? What is it? Point shoes you wear? So when you wear those shoes, what do you notice? Can you give me a little background on this? I don't know who's done more of ballet or not. What background? Like, when you do this, what do you feel in your legs? Physically, what do you feel? Stress, pressure, some sort of force, right? And anybody can do this. Try to stand on your tippy toes for long enough. It's not easy. I mean, literally, you can stand like this. Eventually, your calves are going to get kind of tired, right? And I'm barely on my tippy toes. Ballerinas go all the way up to there, right? So what are they doing? They're taking all of their weight and focusing it on a very small pressure point, right? It's like, have you ever seen somebody lay on a bed of nails before? And you're like, how is that possible? How could you lay on a bed of nails, right? It doesn't make sense. What's happening there when you lay on a bed of nails, you know?
Your like whole body weight is like across the whole thing.
Yeah. Your body weight is distributed. So if there's 200 nails, each nail gets a 200th of your weight, which is not enough weight to pierce the skin. That's why you can lay on a bed of nails. If you're coming to that physics show, we'll actually see a demo of that. This is really cool. It's actually way more extreme than just laying on a bed of nails. I don't want to ruin it and give it away. It's more extreme than just laying on a bed of nails. But the idea here about pressure is that it depends on how much area is being used. So right now, let's pick a random number. Let's say 200 pounds. I don't say I weigh 200 pounds. Okay? That means each foot is carrying how much weight? 100 pounds. I do this now. What's happening? All 200 on one foot. I try to do this. Now I got 200 on like half a foot. So suddenly this becomes a lot more difficult, right? Because I halved my area, then I halved it again, which quartered my area. So if I stand on one foot, holding myself up, I'm standing on a quarter of the area, which increases the pressure by a factor of 4. Because look how area and pressure are related in the formula. Indirect. Less area, more pressure. Less area, more pressure. More area, less pressure. More area, less pressure. Okay, I'm going to do a demo of this a little bit, and it'll help us too. We'll get into a little bit of understanding of this, but that's the common idea of it now. Now, the units are newtons per square meter, but that is defined as Pascal. Pascal was a scientist. He was a scientist, he was an inventor, he was a mathematician, he was a philosopher, he was a writer. This guy was doing everything pretty much, but he was the one who really coined the concept of pressure and did a good job of it.
We learned about kilopascals in chemistry.
Kilopascal is 10 to the third, because kilo. So for example, the atmospheric pressure is 101.3 kilopascals. It's just 101,300 pascals. Yeah, kilopascals are the standard unit that you use in chemistry especially. Or you might use millimeters of mercury, or pounds per square inch, which is called PSI. Or you might say atmospheres. You could say the pressure is 1 atmosphere, 2 atmospheres. I'm going to get into that in a minute, so just hold off for 1 second on that. But yes, you're going to see the relationship there. So the idea, again, is force over area. Now, let me get into the next thing before I get into the examples. I don't want to jump ahead too much. So if we think about, as what Randy was just predicting here, about atmospheric pressure is literally the fluid above you pushing down. What fluid is above you right now? I say fluid because fluids can be liquids or gases. What fluid is above me? Yeah, some mixture of air. Air, I think it's like there's nitrogen, there's argon, there's some methane in the air, there's a lot of different things. But we'll just say air, right? Air doesn't weigh very much. So for us, fortunately, there's not too much pressure pushing down on us. We talked about the can yesterday, remember the can? Suddenly the can's pressure on the inside went down because we put it in that cold water. And the pressure on the outside was more than the inside. So it imploded on itself. So this much pressure, which is called 1 atmosphere, or 1 times 10 to the 5th pascals, or these are all the same numbers, or 101.3 kilopascals. It's the same thing as this. It's also the same thing as this. It's also the same thing as 14.7 millimeters of mercury. What is the mercury? Hg? Hg? What's mercury? Chemical symbol. No one from chemistry? Mercury? Hg? I think it's Hg. I don't know why I think it's Hg. I might be wrong. Is mercury Hg? Is it? It's not an M, I know that, because it's one of those weird ones. Yeah. I don't know there's a Greek reason for that. I forget why. Like iron, ferromagnetic, Fe. So these are all the same numbers. They're all measurements of pressure. The standard unit we will use is pascals, right here. But recognize, because if you pump your bike, or if you go to pump your tire of your car, it'll say 32 psi is probably the pressure you want. So when you hook up the pressure gauge and you start pumping, you don't pump a tire of a car like this, but a bike you would. You pump your bike tire, eventually you look at the pressure gauge and it tells you how much pressure is in the tire. Oh, I hit the pressure I need, I stop adding pressure to it. I stop adding pressure. And the units are usually PSI. In the US, they're always PSI. Okay? But the units that we're going to talk about are pascals. So you always have something weighing down on you. So the next time a teacher says to you, you know, it's a good comeback. They say to you like, come on, there's no pressure, it's just a quiz, right? Just a quiz, no pressure. You say, actually, there's a lot of pressure. 14.7 PSI is always acting on you at all times. There's always pressure on you in life. Right? It's kind of like the whole stop sign one I think I talked about. Yeah, don't actually try that. It probably won't work too well. You can do it if it's a teacher, they might laugh a little bit. If it's like a teacher that knows their science, they might get it too. Anyway, so that's atmospheric pressure. Now, if you go underwater, you feel more pressure. Because now when you're underwater, what do you have? You got water on top of you pushing down, and air on top of that pushing down. So you've got two fluids. The gas, which is air, and the liquid, which is water, pushing down on you when you're underwater. That's why you feel more pressure on your ears. That's why, as we talked about earlier, that's why deep sea divers have to regulate pressure. Okay? All right, let's go to the next slide. Pascal's principle. This is one of our most important principles we're going to learn. We're going to talk about Bernoulli's principle, Bernoulli's equation, and other stuff. But this one really helps to stem all the others, or helps to be the fundamental thing for all the others. So the pressure applied to a fluid in a closed container, key, underline that, closed container, that's the key here, is transmitted equally to every point of the fluid and to the walls in the container. And you're like, what the heck? What does that even mean, right? It doesn't seem to be very clear in the statement. So let me explain what's happening. Actually, no, I don't want to use the demo yet. Okay. So if I had a water balloon, and I started to squeeze on one side of the water balloon, what happens on the other side? I squeeze one side, the other side bulges, right? It kind of pushes out. You can go like this, yeah. It bulges out. Because you're squeezing on this side, right? So the pressure that you're applying is getting transmitted to all the other points on the inside of the membrane, God bless you, which are then kind of expanding, okay? Which are expanding. If you've ever been to a mechanic shop, you probably haven't, but if you have, hypothetically, they put your car up on what's called a lift. A lift. They put the car, they drive it in, it's on this machine. The machine then lifts it like 6 feet off the ground, so they can go underneath the car, study the engine, study the components, see what's wrong with it, blah, blah, blah. For some not crazy reason, but for some reason, a long time ago, somebody thought, this is ideal hydraulics. I can use a little bit of force to create a lot of force and get a mechanical advantage. Kind of like, like a ramp works and a lever works, you get a mechanical advantage of a lever, or a screw gives you a mechanical advantage. So in this case, a lift, or Pascal's principle, is what allows us to do it. There's a chamber, let's slide to the next slide here. There's a chamber underneath the car filled with a fluid. Now, because of Pascal's principle, if I apply pressure over here, or force over here, the pressure generated gets transmitted to this wall, 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 and to here. So I can create pressure over here, which will generate and transmit to pressure over here. So when I push down over here, what's going to happen over there? It's going to lift up, right? It's going to lift up. So let's get to the math behind that in a minute. But before we do that, I need 2 volunteers. Who wants to go? Clemence, come on up. Maria? Perfect. Clemence, Maria, come on up. Awesome. All right. So, let's see. Who weighs more than 2 of you think? You don't have to say the weight, but who would weigh more than 2 of you think? Are you taller? You're about the same size, so it doesn't really matter. But I was going to say the heavier person would stand on you. So, what we have here is a fixed container. It's a syringe. There's water in here. As I draw this up, see the water getting sucked up into the syringe? And that's coming from what looks like a whoopee cushion. It's not a fixed container anymore. That's a problem. TA is not here today. Gus set this off. She did not realize I could put it on well. Alright, so hold on. I need to get no air in this line, so I gotta lower this. So the pressure is high enough. Come on over here if you can. You're gonna take that bladder that's in your hand, and we're gonna attach it to this once the air gets out of the line. We're gonna get these bubbles out of the line. See these bubbles here? No, you don't have to do anything. Just in a minute, you're gonna use the bladder that's in your hand. Hold on. See the bubbles that are coming, climbing?
What?
Get the bubbles out of the line real quick. How far is it? Oh, that's fine. Alright, so I need to get it to the right height. You're gonna have to get that on here and vertical. So it's gonna like twist right out. Alright, thank you ladies for the help. Alright, so let's do this for real now. So we've got this container that is fixed with a certain amount of fluid inside of it. Okay, right now there's a little bit of air on the line actually, it looks like, right? Alright, bear with me for a second, there's a little bit of air here. So step on that end lightly. No, just 1 foot step on it very lightly for now, just lightly. A little more. A little more. Try this instead. Yeah. Yeah, this is fine, it's fine. We're seeing what's happening with pressure. So you gotta step on that edge. As she steps on that end, we're gonna see the water level rise slowly. See it? Keep going in, go. Okay? We want to get all the way to the top. Slowly. Slowly. Okay. Yeah, hold it. Put both feet on. Both feet on. Okay, and when I tell you don't get off right, I'm going to tap this. Okay, alright. So, now, hop off for a second. So what's happening is this. What I want you to see, Maria, come on this side. What I want you to see, I apologize on this, is when Clement steps on here, now you can step on fully. Try to balance yourself, you can use it for it. And just kind of wiggle back and forth so you can put enough pressure in there. What we're going to see is the amount of pressure is transmitted. So this is like one end of the hydraulic press. The other end, so you got to really you got it. Watch, see, take a look at Maria. See the pressure increasing? This is what we're pushing down with right now. Yeah, you got to keep pushing. I'm going to help you out. I'm sitting here. Okay, right now, Maria, go. Push it back. Push it back. So what Maria's doing, believe it or not, is she just lifted Clemence and I, both of our weights, with one hand. Think about that for a second. And we only went up about 1 centimeter. So Clemence was standing and lowered down enough once her weight was there and I helped out. This raised up and she lowered. As soon as Maria pressed down, it actually lifted that side up, and it's hard to even notice, but we did it with Chris Bell in the other class, and you could literally see him moving up when it happened because this side was a little bit heavier, so it pushed it a little further. So when the other person pushed down, he literally went up about a ½ inch. And if you've ever lifted a car before with a jack, that's a mechanical advantage. You sit there and you keep pumping the jack, or you have a rotational jack now, and you might rotate it like, 20 feet in distance, but it only lifts the car about 1 centimeter or so. Thank you. So that's literally what's happening here. You're putting Maria's F1, pushing with very little force. She could have done it, by the way, you didn't have to use a hand, you could have done it with thumb. So with one thumb, she could have pushed this entire syringe down, which would have lifted Clemence about a ½ centimeter off the ground. But how far did Maria push? Maria pushed about, let's say, about 8 or 9 centimeters, maybe 10 or 11. She pushes down 10 or 11 centimeters. You only went up like a ½ centimeter. So the idea is that you don't have to put much force, but it's not going to cause this one to move very far. But it's a mechanical advantage because usually with like a jack on your car, you only need to get the car about 3 inches off the ground to change the tire anyway. So if you push like this, and say you push 6 inches 20 times, 6 inches pushed 20 times. That's 120 inches of pushing, right? And the car only lifted up 2 inches. The 120 you put in, the 2 that comes out, that ratio, 120 over 2 is 60. So you're getting 60 times more strength out than what you're putting in. For that example. The same thing is true right here now for Pascal's principle. Pascal's principle tells us, like we just said that the pressure inside the container is equal at all points. So this is location 1 over here. This is location 2. At location 1, we have a certain amount of pressure. And at location 2, it's the same amount of pressure. A closed container with a fluid transmits the pressure equally. So as a result here, those are the same. Well, the definition of pressure from the last slide was F over A. And now what we're going to notice is, if I want to see how much force Maria was giving, Maria was F1, right? Maria was over here, F1. Let's solve this equation for F1. Solve this equation for F1. So just get rid of A1 by multiplying. Okay? Then because you guys are smart and you know your math skills, A1 is really over 1. I can move A2 down there instead. I can do this. It's the exact same thing. Again, take a look at what I just did. I can take this A1 or this A2 that's down here and just put it down here. It's no different. Whether it's in the denominator, one term or the other, it's the same thing because it's multiplication. So what does this statement tell me? In words, ready? Here's what it tells me. I'm going to point so you might want to look. Maria's force is a fraction, because isn't A1 the smaller part? Isn't A2 the bigger part? So this is a fraction by default, because A1 is smaller than A2. So Maria's force is only a fraction of what she's actually lifting. Again, for hydraulic press, the actual force applied on one side is only actually a fraction of the amount that it lifts. That's the mechanical advantage. The mechanical advantage is saying I can push down with 1 Newton of force and lift something that's 50 Newtons. So the mechanical advantage is 50. 50 divided by 1. I could push down with 20 pounds of force, 20 pounds of force, and lift something that's 200 pounds. That's a mechanical advantage of 10. So the mechanical advantage in these problems, in all types of problems, mechanical advantage is always equal to the input, whatever you physically put in, divided into the output. So we put in F1 and we got out F2. That would be the mechanical advantage in this problem. You lifted a car that was 3,000 pounds by only applying a force of 30 pounds. The car is 3,000. The force you applied is 30. Divide those two. The ratio of those two is the advantage you've gained from hydraulics. This is what hydraulics are. If you've ever seen when the bus, who takes the bus? Anyone take the bus here? Or is taking city bus, right? When the bus pulls over, what does it do? It lowers, doesn't it? And you hear, when you close a lot of doors, when you close a door, the damper in here, remember the damper I talked about? You can hear it. You hear it for a second. There's usually a fluid in a little container that has a disc that slides along it, causing it to be a little bit of a friction force. That's what you're hearing. It's the same noise. It's hydraulics. It's fluid mechanics.
And also for those trucks, you know those trucks that lifts up the...
Yeah, dump trucks.
Yeah.
Dump trucks. Ever see a dump truck lift to dump out dirt? It's like, or cement trucks. When they mix, the cement truck angle changes. Anything that lifts something very heavy is probably using fluid hydraulics here. So quickly, just to make one more statement. Actually, no, this is where I left off in the other class. So weekend, over the given, see what we're doing here. So we've got a hydraulic lift. A 550 Newton force is exerted on a small piston in order to support a weight that's on a larger piston. How much weight can it lift? And what is the pressure exerted on each piston as a result? So the purpose of these examples is to give you guys examples or ideas of mechanical advantages. And we've quickly talked about mechanical advantages in the past, but to give you a little tidbit about it, we talked about like ramps and screws and pulleys. Pulleys create mechanical advantages. They actually have the force that you lift if you use a two-pulley system. In this case, we're going to do exactly that. We're going to figure out how much weight can we lift by only pushing down with 550 newtons. And your answer is going to most likely be bigger than 550 newtons. The whole idea is that we apply a certain force and we get more out of the system. So if we apply a 200 newton force, maybe we get double that or triple that. And we'll see where that ratio comes from. So let's start by listing our givens. So our first force applied is 550 newtons. That's exerted on a piston with 1.5 meters squared. What is that referring to? What is that referring to of the piston? If I see meters squared. The area, good. Okay, 1.5 meters squared. In one or two of your homework problems, the author gives examples with diameters. If you need the area, you take pi times the radius squared. So have the diameter, get the radius, do pi r squared to get the area. But in this problem, I'm giving you the exact area as 1.5. I'm not giving you the radius or the diameter, which would then have to utilize to come up with what the area is. So recognize that this is a little bit of an easier, I think, example than one you may see on your homework or test, if you're given a radius or diameter instead. Now, we want to figure out what force can this lift if that second force is on a piston that has an area of 4 square meters. And 4 square meters, yeah. Remember we did last time? So we're looking in this case to figure out, you know what, is it going to be a lot more, a little bit more, is it going to be less, what is it going to be? And the way we approach this is the same way we approached the hydraulic lift situation in the last slide. We start by saying P1 equals P2. Because the pressure transmitted to a fluid is equal throughout. So we start this problem by saying the pressure applied on the first piston will equal the pressure applied on the second piston. Pressure by definition is what? What is pressure defined as? You can use a formula, you can use words to answer the question. Pressure is defined as what? F over A. Force over area. Now, because I have two forces in two areas, I need to give subscripts. So in this problem, we are recognizing that we have an applied force and a resulting force. There's always going to be an applied force and a resulting force. It doesn't matter which one is F1 or F2, right? It makes no difference, as long as you recognize which area goes with which force. And if I read this problem again, it says that a 550 Newton force is exerted on a 1.5 square meter piston. So these have to have the same subscript. So if I called this F2, then this is A2. Okay? Depending upon what my subscripts are for the force, the area has to be corresponding. So I know this, I know this, I know this, I'm solving for this. It's a very, very straightforward problem. We're always going to be figuring out either the area needed, or the force exerted, or the force lifted, or the area that it's exerted on. It's one of these four variables that we're going to determine for any of these given problems. For this problem, we're trying to find out how much force is lifted, which is F2. How do I solve for F2? Solve this for F2. Multiply A2. I agree, Alex. Okay, bring up the A2 by multiplying it. So literally bring it up over here. And as you guys saw in the last class, we talked about how A2 over A1 or A1 over A2 is a good ratio to use. And we'll see that in a minute where that comes up. Let's figure out what F2 is as a result. Let's figure out what F2 is. So let's plug in. A2 is 4. F1 is 550. So 4 times 550 all over 1.5, which is the denominator. It'll give us an answer of 1466.7 newtons. First of all, let's start with a sanity check. Does the answer make sense? Why? And I don't mean like heavy math, but more general statements. Maria?
Makes sense because force is bigger than the force.
Yeah, and the first force is what the person or machine exerts. The second force in this case is what is being lifted. So the whole concept of mechanical advantage makes sense if you apply less force, yet it lifts more than you apply. That's what a mechanical advantage is. Now, we don't subtract these numbers to find the difference. What do we do instead? We don't subtract to find the difference in the forces. What do we do instead? I want a ratio. Ratio. Divide. Very good, Sarah. So take your answer that you got, right here, 1466.7, divided by 550, please. Steve?
2.6.
2.6 is my mechanical advantage. What I get out over what I put in. And it's approximate, Steve? Probably goes on for a while?
6672.
Okay, so it's about 2.6 repeating is probably the extra number there. So around 2.6 repeating, I'll put the bar over it. That's my mechanical advantage. So that means, and it's logical, it means that I'm going to put in some amount of force and get almost triple the force out. Almost triple the amount of force out. The same mechanical advantage is apparent when you use a crowbar or a hammer to remove a nail. The amount of force it would take to remove a nail from a piece of wood is very great. If you actually just put the hammer there and lift it straight up, it wouldn't work very well. But if you apply leverage, torque gives you a mechanical advantage. Torque is another example that we've seen this year that gives mechanical advantage. Remember the idea of a cheater bar? You put a piece of metal pipe over the wrench to make it longer, and then you get more torque out of it. It's the same thing as a crowbar in a doorway, or if you're trying to get into your house and you lock yourself out, a crowbar can easily open windows even at a lock. It usually breaks them, but it opens them.
So would you say basically all simple machines give us mechanical advantage?
That's the whole idea of a simple machine. Yep. Wheels, pulleys, ramps, a screw, which is really a ramp wrapped around the screw. That's what a screw really is. But they all provide mechanical advantage. Yep.
So is this like unitless, or is it like 2 times 6?
It is unitless. Very good. Unitless. Because what are the units of this? And this? Yeah. It's unitless.
So
Any sort of factor or ratio or factor of increase is always unitless. Always.
So you'd say like it's 2.6 times more efficient with it? Is that like
Sure.
correct?
That's a good way to put it, yeah. Your efficiency went up by 2.6 as a factor, sure. Or you could say you lift 2.6 more than what you put in.
Right.
Yeah? Now, there's another way to figure out mechanical advantage. Anybody see it?
The areas.
Yeah. Take 4, the bigger area, and divide it by 1.5, which is the smaller area, and you'll end up getting the mechanical advantage there. The mechanical advantage itself is not just a ratio of the forces to one another, but also the areas. But you want to take the bigger area over the smaller area. Okay, so 4 over 1.5 will also give me the exact same answer. Okay? It'll give me the exact same answer. So whether I use the forces or the areas to calculate the mechanical advantage, I'm going to get the same thing. Because why is this force bigger in the first place? This force is bigger because I've got a bigger area it's sitting on. So the fact that I'm using this force and this force to come up with it, I could just use the bigger area and the smaller area to come up with the exact same mechanical advantage. The second part of this problem says to figure out how much pressure is exerted on each piston. It's a pretty easy problem. Pressure is force over area. So I can do this force over this area and get the pressure. Or I can do force over area, which is these two, to get the pressure. But either way, the pressure will be the same. If I put a certain amount of force down on one piston, which creates, 20 kilopascals of pressure, the other piston feels 20 kilopascals of pressure. So because it's a bigger area, it's more force that it's feeling pushing up. But the pressure on both pistons will be the same. It'll come out to be a pressure of 366.7 pascals. The pressure will become 366.7 pascals. And it doesn't matter. If I do F1 over A1, I'll get 366.6, repeating. If I do F2 over A2, I'll get the same number, 366.6, repeating. And that's proving the point here that we have a closed system where the pressure is the same throughout the entire system. Okay, the pressure is the same throughout the entire system. Again, tonight, please, when you do your homework for this section, your homework for this section is due tomorrow. This is probably something you didn't do yet, and then you got a head start, and some of you did the whole homework, which is awesome. But if you didn't get a chance to do this part yet, you may have a problem that asks about a radius or diameter in there, or, excuse me, on your test, or I give you example problems in addition to your homework that may have a radius and diameter included. You need to know your area formulas, right? You need to know that the area of a piston that's a circle is pi r squared. If it's a rectangular piston, it's side times side. Right? We need to know our geometric area formulas for circles and squares. I mean, that's pretty basic. With that said, I want to talk about the next topic here. But before I do it, I want to give a quick demo across the room. So let's focus over here on this, whatever this thing is called. Looks like a whoopee cushion. Now, there's some water left in here, so it'll still work. It's not working as well as I hoped because I did lose a little bit of water in the class. So first, let me just remove this guy.
You're just showing me.
Yes. Take a look. Take a look at the water dropping. You see the water drop? It's continuing to drop. And where did it stop? It stopped right there, right? And where is the bladder that's providing the water? Take a look. It's around the same height, isn't it? If I lower the bladder, what happens to the water level in the line? If I raise the bladder, look at the water level on the line. Following you? Can you see it from there? Is it apparent? What happens? Literally, it mocks the height that I'm moving to, right? Now, the reason, the rationale we're going to see in this section here, if I were to literally go a little bit further up, the water starts to shoot out. Now, if hypothetically, I'm not going to shoot all the way. Okay. If I keep raising up a little bit, as it raises further and further up, I'm going to see the water level continue to rise up. Until eventually, if I go far enough up, what's going to happen is the water's going to spill out. The minute I lower this, it's decreasing the amount of pressure. Again, the water weight in here, physically, this weight to the water is pushing down, which is pushing this back up. But if I lower that water weight, I have less gravitational weight because I'm closer to the earth. Here, I have more gravitational weight. And the idea is potential energy, really. And the potential energy in a line is what's causing this water to rise or lower. Now, you've seen these before. I think I have to, if I lower this, yeah, it works. Okay. You've seen these before when you're driving. If you've ever driven on the New Jersey Turnpike, or for the most part outside of New York or Long Island, you see the water towers. Anybody, can someone describe what a water tower looks like? Because there's a specific thing about it that is important in computer.
That looks like a bowl, almost.
Okay, give me more about it.
Like
Is it on the ground? Is it above ground? Is it below ground? Where is it, Peter?
It's on the ground, it's like tall, and it has like a circle, like over the top.
Yeah, so it's pretty tall. It's usually sitting on some sort of a structure, and then the actual water tower is a little bit higher than the structure. Why do you think the water tower is above the ground level? Why would the water tower be above ground level?
Keep pressure high.
Yeah. The higher the actual level of the water, the more pressure it's putting on the hose or the line. So in this case, you can simulate what a water tower does, literally. So a water tower, when the spigot is open, so right now the spigot is closed. My thumb is the spigot, so it's closed. But when the water tower is above the water level, it literally just pushes the water out. And this will continue to happen until I lower this enough, and then the water level is the same here. And again, and look, I ran out of water in the bladder. Take a look at the water in the hose. See how they're pretty much at the exact same height right there? Because the pressure is equal on each side of this bend. This is a U-shaped barometer. This was the original, the original way that air pressure was measured using barometers. It was a U-tube was the name of it. Not U-tube, but a U-tube. And it's a barometer. It's pretty much a glass piece of piping, in a sense, that's glass that looks like a U shape. And the more pressure the atmosphere pushed down, the more that mercury would rise up, and we can measure the pressure in the air. Every day we have atmospheric pressure, but it varies a little bit. If there's more condensation in the air, if there's more particles in the air, there's more pressure that day. And that affects storms. High pressure centers, low pressure centers affect where storms come into play. So we need to know how to measure pressure at all times. So barometers were invented a long time ago, and it used to be just one little cylinder pipe with a pool of mercury. And that pool of mercury, when more pressure was, would fly up the actual thing. It would physically push it up further. I put a video under news forum about this because James Donarski asked about it in the class. He asked, like, oh, how do they even work though? So I put a YouTube video about the history of barometers and where they came about and why they're such an important tool. And they really are. Without barometric pressure, we'd have a lot of problems. Tires wouldn't work. Hydraulic presses, your cars wouldn't work. Pressure is in literally everything. The door that stops, the piston in the door that stops it from slamming involves hydraulic pressure. So without pressure, we'd be lost in society. Buildings would not be able to stand without pressure. A lot of
hurricanes will sneak up on us.
the pressure centers that we notice actually are one of the things that cause hurricanes to come off the water.
That's what birds.
Is it low or high pressure? You know which one?
It's typically high pressure.
High
When
pressure.
high the storm, it's like way low pressure. And that's when birds and other animals are able to sense it a lot higher than we are. So they'll sense an atmospheric pressure change and they'll run because they know that the storm is coming. That's why you ever see in movies like all the birds are flying away because they know something's coming. They sense the pressure.
That actually is absolutely right.
Yeah.
I've heard that before. And I'm thinking also about like animals with pressure sensors in their body, like natural pressure sensors. Where we do too. We just don't sense them as finely tuned. Yeah. So like, yeah, you might feel pressure when you go on an airplane, right? Have you felt your ears pop before? Why do your ears pop? When you go on an airplane, it's lower pressure when you get higher in the altitude. So it's low pressure. If you've ever been sick and had like a sinus infection, you go on an airplane, you'll feel your sinus cavities clear out completely. Because all the pressure that was in there is much, much lower suddenly because you're taking off an airplane. But when you land, you might feel that pressure intensify when you're landing. Because there's more pressure lower. And that makes sense. The lower you are on the earth, there's more air weighing down on you, so there's more pressure pushing down on you. The higher you are, there's less air above you pushing down. It's the same thing as swimming in water. When you swim deeper in water, there's more pressure because there's more water pushing down on you. When you're at the surface of the water, there's not as much pressure. So it's the same concept here, that as I raise up the water tower, I'm increasing the height, which is increasing the pressure in the line, which causes this to release the actual fluid. Eventually, obviously, if I wanted to, I want to do this, and I can get this above the entire way, all the water will drain out of it. I have a little bit in this little tube here. And I can get that out by just doing this, and just moving this a little bit further. And now there's literally no water left in this line.
Well,
Almost.
why is it stuck?
This is why it's stuck. This end of the line is still fixed. If I do that, now the entire thing flows out. So there's no water really left. Something like that. The idea behind this, though, transmits into also what you've done with straws. Where'd that paper towel roll go? With straws, right? If you used a straw before at some point in time, the way a straw works is by differential pressure. When you suck on a straw to bring like the soda to your mouth, you're creating a vacuum in there. That vacuum in the straw is a lower pressure. There's higher pressure below the straw, which is forcing the fluid up the straw. If you ever put your finger on the top of the straw and take it out of the water, and you ask yourself, how is the water still staying in the straw? And then when you take your finger off, it falls out, right? When you put your finger on the top of the straw and lift it out of the water, there's pressure acting on that fluid from the atmosphere from below. But your finger is there to stop the pressure acting from above. The pressure from below is enough force to combat the weight of the fluid. It keeps it from falling. The minute you remove your finger, you got pressure above, pressure below, which are in equilibrium, and then the weight of the water will just cause it to slide right out. So it's the fact that the pressure below the actual straw is pushing up with enough force to prevent it from falling out because of its alone weight.
Have you ever heard of the thing where some people get like long tubes, put it in a gas tank?
Yeah. Siphon?
Yeah.
Siphoning gas? Yeah.
It's similar to that.
That's exactly it. They're creating a pressure differential. So the way siphoning works is that you start like you put it in open someone's gas tank. Nowadays gas tanks can't be opened as easily. Like you pry into someone's gas tank, take a hose, put it in there, and you start sucking on one of the hose. As soon as you get enough gas out, you can obviously drink it. As soon as enough gas comes out, there's a lower pressure differential than inside there, and it'll force the rest of the gas right out. Siphoning gas is the word for it. Yeah, siphon gas. Justin, do me a favor. I know you're doing that. I don't know where paper towels. I have a whole roll of paper towels in here. Nobody sees them, right? Paper towels, paper towels. There's a lot of water I just spilled right in front of the sink. So just don't step on it. Watch your step, man. You can just get it, clean it up, Gus. I'm sorry about that. Thanks, Gus. So let's talk about how this works now. Let's go into the physics of how this physically happens. So we're going to start with a little derivation. You could watch if you want. You can feel free to watch. I'm going to show it. If you want to write it, you can. It's not going to be fair game for the test. So the idea at the end, the conclusion we draw, will be what we'll use for the test. But I'll show a quick derivation. So let's start with the definition of pressure. Pressure is force over area. Now, if I'm talking about pressure that varies with depth, then that means as we go lower or further down, we have more weight pushing down on us. Imagine diving deeper into the water. The deeper you dive into the water, the more water pressure is pushing down on you. So as a result, we can recognize that this is really a weight pushing down. It's a force of gravity pushing down. Gravity, by definition, is equal to mass times g. Mass, by definition, is density times volume. And we did this in the last couple slides, if you're not recalling this already. We replaced mass with density times volume several times. Okay, you got to get used to doing that, obviously. Now, here's where it gets a little bit tricky. Here's where it gets tricky. Let's picture this object as a brick. It's easy to do it this way. Imagine a brick that's underwater. So I'm going to go ahead and draw a picture of a brick. I've got my brick. It's underwater. Here's the water level right here. Now, the idea behind pressure is that it's the weight acting on an area. It's the weight acting on an area. Now, the brick itself has several areas. It's got faces on the side, it's got a face on the bottom, it's got a face on the top. We are concerned with the pressure as we go further and further down in the water, which means we're really focused on this area right here. That's the area that we're focused on. Now, if I want to focus on that area, it means I need to only consider a column of water that's directly above the brick. Yes, there is water all around the brick. I take a brick and throw it into the ocean. There's water all around it. But the water that's directly above that red area is what's pushing down on the brick. The other water, oh bless you, the other water is pushing in from the sides. But we are concerned with the pressure as a function of its depth. So we are concerned with the water pushing down on the top of the brick. So go ahead and do this now. Extend each corner of the top of the brick up like this. Extend each corner up like what I'm doing here. And this column that I'm drawing might not look like a column to you, but it is a column. The columns don't have to be cylindrical. A column can be rectangular. This column of water is pushing down on this area right here. Now, VF is the amount of the fluid that's actually pushing here. VF is the volume of the fluid physically pushing down. What's the volume of a rectangular solid equal to? Math class. Volume of a rectangular solid equals, Steve? What is it? If they're different sides, what do I use? Good. And they're different here, so, right? This is clearly different. So I'm going to use LWH. So this is the length, this is the width, and this is the height. Length, width, height. So the volume in this case, the volume of the fluid pushing down is really LWH. But what's the area of the brick in red? The red area of the brick. Look at it, please. What can I replace area with there? It's obvious for a reason. Yeah, length times width. It's not an accident. Here's what happens. LW cancels. So it turns out that the width of the brick, the dimensions of the brick mean nothing. I can be underwater like this, or underwater like this. If I'm at the same depth, my surface area that the water's pushing down on means nothing. The LW don't matter. So all that matters is the density of the water pushing down on you, the depth, let's write a note, H is depth here. We're going to call it H though. I know you think H is height. We're going to still call it H. Every physics book from this point on will call it H. Not to confuse you with D for depth. D is also distance, right? D later on can be something completely different. So we don't use D for depth. We're going to use H for depth. It's the height of the column of water, which is the depth. So this turns out to be, again, density times gravity times the depth. That's the amount of pressure acting on you from the fluid you're in. So right now, what fluid are you in again right now? Air. Air has a density. Right? Everybody, air has a density. That goes here. 9.81 goes here. The question becomes, how far up does the air start? Which is really the height of the atmosphere, right? Think about it again. How high is the atmosphere above us? It's however high the atmosphere is in meters, that's how much is pushing down. That would go right here for H. If I were to figure this out, find the density of air, gravity, and if I knew the height of the atmosphere, it would come out to be atmospheric pressure. 101.3 kilopascals, that number that I referenced in the last class. Now, this is just the pressure acting from one fluid. But if I'm underwater, physically underwater, I've got the water pushing down on me, but what's pushing down on the water? The air above you, the air pressure, the atmosphere. So if I really want to do this, I'm going to go a little further. This is not the end of this slide. This is not the formula I'm going to give you on tests. This is called gauge pressure. But really, we want to figure out the total pressure, which is equal to this. Again, this is gauge pressure right here. But we want to tack on to that the atmosphere. And this is the total pressure acting on you. So when you're standing right here, you have only the atmosphere acting on you. That's your pressure pushing down. Again, when I'm standing right here, P0 is pushing down on me. But now I take a dive into a pool, I still have the atmosphere pushing down in the pool, but then the pool water pushes down on me. So it's the sum of these two values that will give me the total pressure when under the surface of a fluid. Again, when under the surface of a fluid, the total pressure will be the fluid pressure, also known as gauge pressure, the fluid pressure itself that is in, plus the atmosphere pushing down on that object. When you measure the pressure in a tire, you're measuring what's called gauge pressure. You're physically measuring the pressure inside the tire. You're not accounting for the atmosphere. The atmosphere is not weighing down on the tire. Yes. Depends on the scenario. Again, if you're measuring the pressure in a closed container like a tire, and you have a pressure gauge on it, you're measuring this right here. It's called gauge pressure. You wouldn't use this formula, but that's what you're measuring. But if you're measuring anything below the surface of a liquid, primarily liquid, a fluid in general, but primarily a liquid, then you have the atmosphere plus the liquid pushing down on us, both. Okay? So it depends on the scenario you're looking at. Let's look at an example of this to see how the math works, Belen. Okay, and P0, by the way, write yourself a note if you need to. P0 is on your formula sheet. It's a constant. Okay? It's a constant on your formula sheet. This formula circled in yellow is also on your formula sheet. So what's circled in yellow is on your formula sheet, but you need to know what these things represent. You need to know, on your formula sheet, it doesn't tell you that this is total pressure. It doesn't even say that this is atmospheric pressure. You have to know what P0 stands for. Yes, the number is written at the bottom, but you should still know what it physically means. And then, what is H? H is depth. That's a big problem a lot of test students have because they look for the word height. And height is not given in any of these problems, right? The word depth is used. And then the pressure of the density of the fluid itself is there. So let's look at one example of these. The example says, calculate the depth in the ocean at which the pressure is triple atmospheric if the density of seawater is 1025 kilograms per cubic meter. So we have to think about what we're given, what we're looking for. Thank you. So what are we given in this problem? What are we given? Let's start with that. Get Alex, give me something.
We're given the density of the fluid.
Okay, the density of the fluid is absolutely given. What else? What else? Chris?
I think actual pressure.
Actual pressure should be what number?
3 times 1 times the constant.
Very good. Well done, Chris. That's the tough part. Most people have struggled with that. The other classes took a little while to get to that. Let's talk about that for a second. It says, calculate the depth, so find H, calculate the depth at which the pressure is triple atmospheric. The pressure is triple atmospheric. The pressure is triple atmospheric. So that statement is absolutely correct. So I'm trying to figure out H in this formula here. I'm trying to figure out H in this formula over here. I know P. P is 3 atmospheres. That's how much pressure it is. Right? Again, I know that the pressure we're looking for is when is this triple atmospheric. So technically, we can move one of these POs over. 3P0, I can move one of them over, leaving me with 2P0 on the left-hand side. Just like common terms, right? Common variables or like terms. We can subtract P0 from both sides. And this equation becomes 2P0 equals rho GH. And then go ahead and just solve for H. Okay, divide by rho G on both sides. Divide by rho G on both sides. So this would absolutely be the approach we're going to take now. Some people in the other class got confused because I started using things like 3P0. So originally Chris said you were starting to say 101.3 or whatever the number was, and he's like, let me just use the constant. But if you wanted to, you could literally plug in 101, 101,300 pascals. You could plug in here 101,300 pascals. You could get a number for this one, get a number for this one, plug in the number here, plug in the number here, and solve for H. So if you don't like solving algebraically, go back up to the first blue line we have here and plug in all the numbers we know. We know P0, we know rho, and we know G. So we could have plugged in here, 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 and here. We know all those numbers. So if you don't like solving algebraically and getting this answer at the bottom here, plug in where you see those 4 arrows. Okay, plug in where you see those 4 arrows. The answer is going to be around 20 meters. Around 19.9 meters. And again, I know it's meters because I'm looking for depth. I'm trying to figure out the depth below the water level for which this happens. And the depth below the water level. How could this problem vary? How could this problem vary? Yeah, Mary. Whatever you would think. You were thinking right away. What else could change, Mary? It could be anything. There's infinite answers right now. Good. It could be a different fluid. It's not salt water. Maybe it's an unknown fluid, and I give you everything else and say, what is the fluid? So then you're just solving for rho. What else could vary?
Do you just plug in 9.81 for gravity?
Make sure parentheses surround this, guys. If you didn't put parentheses around here, it's not going to work. Right? Because this is a product and a denominator, it needs parentheses around it always. Whenever you have a denominator with a product, a sum, or a difference, you need parentheses around it. What else could vary, Catherine? Exactly. It could be like, you know what? Find the depth when it's 5 times atmospheric pressure. And how would that change? This would become a 5. When move this over, it would make this a 4. Would you make this a 4? And that's it. That's all that would change. That's why this generic solution is pretty powerful, right? Because I could just vary stuff up. I could say we're on Jupiter now, and this becomes 26.1 instead of 9.81 because I'm on Jupiter. Or I'm on the moon, 1.6. I can vary whatever I'd like to in these cases. Yes, I know there's no atmosphere in Jupiter.
No. Do you think that's how they use, like that, they just auto-calculate that for depth monitors when people are
Absolutely.
diving?
Yeah, it's a computer program. You're doing it in robotics right now in the class, right? You write a program, but more with coding, that allows them to be called parameters.
Yeah.
And you vary the set parameters. So the parameters that vary here could be height and depth, 10 meters, 15 meters, 20 meters. So you take one formula and you just keep replacing H and you get the pressure at each level.
Yeah.
You wouldn't recalculate it a million times. It's an algorithm that does it for you. Yep. That's literally the idea behind computer programming. That's exactly what it is. It's varying one thing to iteratively change. So you keep doing the process over, and you just vary one of those parameters each time. Again, we could have varied other stuff, right? Instead of saying it's water, we could have said Jupiter, we could have said a different pressure, or maybe we could have been given a height and figured out the pressure below that value, which is the easiest approach, right? If I give you the depth and gravity and the density and you have the atmospheric pressure, you can find the overall pressure just by plugging it into that equation and getting your answer. That would be the easiest form of that answer. Okay, we have a quick break. Take a 3-minute break. Come back to your lab. Okay, here's the homework. You guys know it's due tomorrow. You should have already started it. Some of you already turned it in, which is awesome. Okay, but make sure that you take a look at this tonight.
Right now?
Yeah, so 10
Oh,
minutes.
so they're not even testing the first one.
The first 20 minutes, they're designing 10 minutes and building 10 minutes.
Oh, makes sense.
Making it
I
all
might just
your-
ask her to just come back right away.
Yeah, but if you want, I mean, I don't want to take you away from it too much. I don't need you the first minutes. I don't want you the first minutes. Because I take a less time.
No, she doesn't care.
Don't talk.
I know, I haven't talked to her. I would never go
But
up.
the volunteer is saying that you can stay for the first 20 minutes if she thinks it's important, and then come back for the second 20 minutes. Because I really don't have much for you to do in the first 20
No, I
minutes.
know.
So you don't have to be here 100%.
I know.
But the second 20 would be ideal, Gus.
I'll ask her.
Thank you very much, Gus.